All right, let's talk about isomers. I think I'll need that. Got everything showing where it should be. Right. It's up here. All right. Isomerism is such a huge topic that Dr. Carty has divided it in his textbook into 2 chapters. But since our schedule is so compressed, we're going to have to cover both of them at once. All right. So we need to have a way of organizing how we approach isomerism. We need to define it first. If you compare 2 molecules, say you have a molecule that's got the exact same molecular formula as another molecule, that doesn't tell you anything about the structure. And in organic chemistry, as in most chemistries, structure is essential to know how the molecule will react. So in organic chemistry in particular, we need to know something about the structure. 2 molecules are said to be isomers if they have the same molecular formula, but they're different in some way. And there are a number of ways that they can be different. So this flow chart divides things at first division is connectivity. What we mean by connectivity is how are the atoms connected with one another? A perfect example, if we have, let's see, C2H6O. We have that formula. It could be, I'm going to write it out, CH3, C, let's see, H2O H. Is that right? 1, 2, 3, 4, 5, 6. Yeah. That's ethanol, right? The drinking kind of alcohol. But we could also write it this way. We could put that oxygen in the middle. Put the methyl groups on the outside. Let's see, that would be 2 carbons, 6. Yeah. This is dimethyl ether. They're 2 entirely different molecules, but they have exactly the same formula. So the connectivity here is different. Like this oxygen is connected to 2 carbons, right? But that oxygen is only connected to 1 carbon and 1 hydrogen. So that's what we mean by connectivity. How are the atoms connected to one another? If they're connected exactly the same way, but they're different in some other way, we call them stereoisomers. If they're connected in different ways, like these 2, those are called constitutional isomers. Okay, and they go off, this comparison goes off on a separate leg. They're just completely different. What we want to focus on in this course and in organic chemistry in general is the stereoisomers. So if they're all connected the same way, then maybe they're different in some other way. Okay, one way that they can be different is if we have the same molecule, and they're single bonds, and you just get rotation around those bonds. So at any one split second, they could be in this position or that position, or they could be over here in this position, rotating around one of those single bonds. That means that they're conformers. Now, I know what you're thinking. You know, what's the difference, right? If they spin around like that, how do you know? Well, it's an idea, it's probability. Because if they spin around that single bond, which they can and do, maybe they spend more time in one position than the other. Largely due to steric hindrance, that is, large groups getting in the way, keeping them from spinning too much to one side. They tend to stay in one place. They'll still spin, but on average, they're more likely to be in one position than another.
Does that have to play with like sigma and pi, like the movement at all? Or is
Yeah.
that just like, or is this completely different from sigma and pi?
Well, yeah. That would be if you had like this. Let's see. One, two, three, four. That would be it. This would be a completely different. This would be a constitutional isomer.
So
And
that one
it
wouldn't
would
move.
it would not rotate. No,
Okay.
it wouldn't rotate about. It might rotate about this bond. But when we're talking in organic chemistry, when we talk about isomers, we talk about carbon-carbon connectivity. Right? And all these others are functional groups that are side groups. Right? So we would focus on this bond right here. And since it can't move, this molecule doesn't have any conformers because it can't rotate. But if it was a single bond, yeah, it could rotate till cows come home. Okay, so we've got isomers. They're different in some way. If their connectivity is different, then they're constitutional isomers. If their connectivity is exactly the same, then they're stereoisomers, and we have to look for other differences. Conformers are rotate around a single bond, and we're gonna look at a way of we call them projections. There are different ways of visualizing three-dimensionally these molecules. They're called projections. And there are different types of projections that work best for different types of molecules and isomers. So we're going to get to those for the conformers in just a minute. The configurational isomers are the atoms are connected the same way, but they're not connected in exactly the same positions. The wedge dash way of writing a molecule is a good way to look at this. So if you have a carbon in the middle, right, and we have say a hydrogen out here, and then in the same plane we have let's see, we have a chlorine there. So then we have potential for one going back here and one coming out here like this. These are in the same plane. This one's back and this one's forward. Okay. So if we put something else over here, like say we put another methyl group. And over here, we put let's just put an iodine. Okay. If you have a carbon with four different attachments, four different atoms or groups attached to that carbon, then you have the potential for at least two configurational isomers. And that is, they're connected the same way, right? This carbon is always connected to that hydrogen, chlorine, iodine, methyl group. But if instead we put the methyl group in the back and the iodine in the front, that's an isomer of the other one because they're not in the same position. Right? They're configured differently. They're connected the same way, but they're configured differently. And if we had, we probably ought to use models. Yeah. Let's get our models out. grab a model set.
So the other day I went to Walmart and I was at like the game section, but they had this atom thing that you can move it like, it's called an atom, something like that, but it had like balls on it and they can move it around. So is that kind of like what you're like, you probably don't know what I'm talking about because you've never seen it, but like in my mind, that's how that those are moving.
Can the atoms be detached and reattached different ways?
No, they just kind of attach to a string. They move from one end, like they just keep moving, if that makes sense.
Yeah,
You'd have to
see
see it. Okay.
Yeah, I'd have to see
Because
it.
like in my mind, I guess that's how I'm thinking they would move.
They get to this position by the way the reaction goes. The reaction that produces that molecule gives you this isomer. Sometimes the same reaction will give you both isomers in 50-50 proportion. Sometimes it's 30-70, sometimes it's 10-90. And there are various factors that feed into that, but they are different isomers, configurational isomers. Yeah. Now, we're going to talk a little bit more in detail later about enantiomers and diastereomers. All right, so we're not going to focus on that right now. All right, so we covered the connectivity already. So on the left, we have the dash wedge representation of an ethane derivative, right? 2 carbons. Now, maybe some of those X's and Y's, they could be methyl
You're
groups.
on the same slide.
It's up there, but I was gonna say something about that.
Oh. Well. Acting up again. We might have to just ditch that and use the backboard. Because I don't want to waste time going to get help with this. Yeah, we'll just do that. We'll spend our time on the backboard. There we go. All right. All right. Are you with me so far?
Yeah.
In spite of that glitch.
I was a little confused at first, but I understand. I know where we're at now.
Okay. So if we do a dash wedge setup, it looks like the one on the left. But if we turn the molecule, if we rotate it 90 degrees with X's toward us, no, Y's toward us. They put the Y's in the front. And we're looking down the axis of the bond between the 2 carbons. That gives you a Newman projection. This, and I'm sure it's named after somebody, Newman, something or other. What it does is it allows you to assess the arrangement of atoms in a conformer, right? Because you got that single bond between the 2 carbons, so this thing can rotate. But at this instant that we're looking at it, the Y's are in the front and the X's are in the back. So when we draw it, we always have this circle. And then the front comes out of the middle of the circle like that. And then the back is behind the circle like that. That's the way you view it. So since we turned it with the Y's in front, these Y's are here and the X's are in the back. And the carbons are here and behind. And there's a single bond between the two carbons.
So what's the X again? What would that be?
That could be anything. We could make something up. Yeah, we can make something. Let's say we have say a chlorine there, and a iodine here. And in the front, we have maybe another methyl group. And we have a methyl, let's say we have let's say that's a hydrogen. And let's make this a hydrogen also. Okay. So if we wanted to rewrite this as a dash wedge, right? Then we would take this and rotate it 90 degrees to where the bond between the two carbons now is like this. Okay. Okay. So if we rotate it like that, then what's going to be in the plane? Right? On this side over here, this plane is going to have the methyl group. Right? And then this hydrogen is sticking out. See, this hydrogen is sticking out, and this hydrogen is toward the back. Right? That hydrogen is here. This hydrogen is here. This one is on the plane. So if we look at the backside the same way, then this one is going to be opposite that one. Right? So it's in the plane. And then that means that when we rotate it around like that and put this one in the plane, this one's going to be in the back. See, is that down here? Yeah. This one's going to be in the back. And this one's going to be in the front. Oops, that's iodine. Sorry. So if we,
I'm having a hard time visualizing the 93 term.
yeah, let's
That's what I'm not getting. But
let's build the molecule. I think that'll help.
what is
Well, it's got two carbons, right? Two carbons right here. And we've got two hydrogens and a methyl group in the front. So let's see, I'm gonna turn it like this. So those two hydrogens are right there. Like that. And then down here is another methyl group. So I'm gonna put this. And there's another methyl group down here. I'm not gonna put hydrogen on it because it'd take too much time. That shows the front. Let's see. Yeah, the front. Now in the back, we've got chlorine sticking up. I think chlorine is yellow, isn't it? No. Chlorine's only got one bond. All right, so I'm gonna have to pick something else. Red's oxygen. All right, I don't have that color. Let me grab another set. Because it's the halogens are only supposed to have one bond.
Oh, okay. And that bonds, you're talking about the whole thing.
Yeah, the holes. Right, single holes. Yeah, this doesn't have it either. Oh, there's a purple. Yeah, purples are good. I'll stick the purple on there. Okay. And then another chlorine down here. So, well, I don't have another purple. Yeah, I do over here.
Then I'm gonna make, what is blue? Can I just use blue?
Blue has three bonds on it. Blue's nitrogen. You can use whatever color you want, as long as you're consistent. Okay. So far I've got my hydrogens here, my methyl group here, and in the back, I've got this chlorine sticking up. Let's see. Wait a minute. Something wrong with that carbon. Oh, that's an sp2 carbon. I don't need that one. Here we go. I need this one. Oh, that worked all right. Should have left it alone. There we go. So then on the back, I've got this chlorine here, and then I've got another chlorine over here, like that. And then I've got an iodine. So I'm going to use yellow for my iodine. All right. So let's see. In the front, I've got my carbon in the front. I've got the hydrogen here, hydrogen there, methyl group here. And in the back, I've got a chlorine here, chlorine there, and an iodine over here, like that. Okay. So 90-degree turn would be like this. That would put the methyl group in the plane. That would put this hydrogen out, this hydrogen back, this iodine out, this one in the plane. It's actually the same plane as this methyl group, this chlorine in the back, and this iodine in the front. That's what that 90-degree rotation did for us. Okay. Now, we know that these bodies, these atoms and molecules, components can spin around that single bond. So we could say, all right, what would it do if it did like that? Yeah, just rotated 30 degrees. What that would do is it would put this iodine and this methyl group close to one another. You get some steric hindrance because there are hydrogens sticking out of this thing that I didn't show. All right, so it's probably not going to spend a lot of time there. It's going to want to rotate all the way around to this, like that. Okay, and that would still be somewhat hindering to this one. So if we rotated that way, that's not good. Rotated this way, it's still hindering this one and this one. All right, that's hindering again. So the ideal, actually, the one where it's going to spend most of its time is probably like that.
Hindering is where you would have two right in front of each other.
Yeah, and if they're very large, they're closer than they were before. And that means that they're trying to occupy one of each other's space. Steric hindrance.
So what you're saying is like they're all constantly kind of like rotating like this. Both
Yeah.
of them are just like one. Like are they both simultaneously moving together? Like both of them, or is it
Yeah,
just
I mean
one?
they don't detach from one another,
Yeah.
so they spin around that bond.
Yeah. Okay.
Right. But also, since we've got this group down here, right here, it can spin around that one too. So you have to focus on one or the other, right? If we wanted to do this one, right, we could do like that. Then we have these hydrogens out here like that. And it'd be a different Newman projection. All right. This is not easy stuff. I'll grant you that. And it's not easy for me either. It takes a lot of work. And actually, those who are good at using these projections are specialists in a certain area. And they use them because they help them understand and predict for their particular discipline. Right. So there are people that use Newman projections all the time. And they can think in those terms. Whereas others probably don't use them that much. Okay. So these are known when we position the molecules a certain way, like this. When we position them a certain way, there are angles that can be measured. These are known as dihedral angles. They correspond to the angle between a CX and a CY from the other carbon. So what's the dihedral angle here? Right. The dihedral angle between this one and that one, looking down the axis. So it's like when you project, you're flattening this 3 dimensions onto 2 dimensions. So now you can look at this angle. What's that angle right there? Well, the simplest angle is, what is that? This is 90 degrees. That's about 60 degrees between these two. Right? So if we extended this down like that, that angle is 60 degrees. That's the dihedral angle for this conformer. If we want to measure the dihedral angle from this one to this one, that's 120 degrees. If we want to measure the dihedral between, let's see, this one and that one, right, that's 180 degrees. Okay. And you can keep going all the way around to 360. That's what's meant by the dihedral angle. As you take with a Newman projection, like that, you take 2 of the groups. In fact, you could take these 2 right here and say, what's that angle? That's 120 degrees.
Wait, do that again.
This one, the dihedral angle between this one and this one is 120 degrees. I think that's the easiest one to recognize because 120, 120, 120 makes 360.
Yeah.
It becomes a little more problematic when you try to do the dihedrals between a group attached to the back carbon and a group attached to the front carbon. Then you really have to use your imagination.
And in this case, you're looking at it always using this Newton's one. When you're
Right.
looking at
The Newman, yeah.
Newton.
Yeah, it's like these projections are they're like 3 dimensionals squashed into 2 dimensions. That's the way it's represented. That's why they call them projections, because when you project something on the screen, it's only 2 dimensions. All right. So, what would be the Lewis structure of the molecule with the following Newman projection? All right, that was pretty simple, actually. Because it's only got 1 methyl group, the rest are hydrogens. Okay, you got to recognize how the projection is presented with a carbon in the front, a carbon in the back, along the axis. And then if we're going to do the Lewis structure, you have to rotate it. And I assume they're talking about the dash wedge. Oh, they're not going to do it for us. Are they going to make your instructor do it for you? Okay. Let's see. This projection, okay, the methyl group is still there. The rest of them now are hydrogens. Now I better redo that. It's too messy with all those dihedrals in there. So we have a circle. We have that, this one, this one, this one. We have a methyl group down here, and the rest are hydrogens. Okay. So I'm going to save myself some time and leave it that way, because that's generally how it's going to go. You take this, rotate it like that. That puts, I like to think of it in terms of this methyl group is in the same plane as this carbon bond. Right. That means that this group is in the same plane. That hydrogen is in the same plane. And that means you've got these other two hydrogens here and here. Okay, so that's the way I would see it. Okay. Now let's see if, let me read this and see if Dr. Carty has simplified it anymore. Which atoms are connected by the bond not observed in the Newman projection? The bond not shown is the carbon-carbon single bond, right? Front carbon is represented by a point, and the back carbon is represented by a circle. Okay. What atoms or groups are attached to each of these atoms? Okay, the front carbon is bonded to 2 hydrogens and a methyl group. The back one is 3 hydrogens. Okay. Well, I don't see how that helps.
On the exam, when we have questions like this,
Mhm.
could we have these, like, to help us with this?
That's a good idea. Yeah.
Okay.
Yeah, we'll have a set here. Have you got a set at home that you can practice
No, I
with?
forgot to order one.
I sent mine to my house in Morgantown. I ordered it on Amazon and it didn't change my shipping address. So
Oh,
it's with my neighbor.
you know what? We've got such a small class. Why don't you take a set with you? Keep a set at home.
Okay.
Because we've got enough and we'll have a set here and one at home. Just remember to bring it back. And don't let your cats play with the pieces. Y'all have cats? No? Oh, well, never mind. Okay. All right. What this plot is trying to tell us is that using the Newman projection, if you rotate, this is another way of saying, of introducing the idea of steric hindrance. Notice that the highest energy, which is the least stable, is an eclipsed type of arrangement. So when you're looking down the barrel, the eclipse is going to be rotated so that this group is in front of that group, and this one's in front of that one, and this one's in front of that one. That's an eclipsed conformation. Those are higher energy situations. And molecules, chemical reactions, molecules alike, don't like high energy. They like the lowest energy possible. So you're going to have the low energy dips is where you're going to have the ideal. If all of these are hydrogens, then the first, second, and third dip are essentially the same. And wherever you get an eclipsed conformation, you get an increase in the energy. It takes energy to get them to that point, and if they stay there, then they're going to be unstable. They want to roll down to either side of that hill. So this also says that the dihedral angles 0, 120, 240, and 360 are all high energy dihedral angles. Okay. All right, so I used valleys as, uh-oh. Catch it time. Yeah. So you have two possibilities, staggered or eclipsed. Now, if all the attachments are identical groups, then you're going to have similar peaks and troughs as in terms of energy. But if you have different groups attached, then that diagram is going to show some of them are going to be very deep troughs and some are going to be shallow troughs for eclipsed conformations. And the eclipsed conformations where you have the most steric hindrance are going to give you the most unstable, the highest energy positions. Say if we had another methyl group, say on the back one, like here, the methyl group here and here would be ideal. That would be the lowest possible energy for this molecule if we had a methyl group here. Like that. They would be farthest apart from each other possible. Less interference. But if we rotated around where the methyl groups were eclipsing one another, that would be the highest energy possible eclipsed conformation.
So that right there is ideal though.
That's ideal.
Okay,
Yep.
and then if it was kind of rotated a little bit, it would be.
If you rotated this around like that, 90 degrees, and put this methyl up here, then they would be too close to one another. They would be interfering, sterically hindering one another, and that would raise the energy of that conformation to the highest level of the trace. If you did one of these traces, then that one would be a very high peak. This one would be the lowest peak. And then other conformations where you have, if this eclipses that, that would raise the energy, or this one eclipses that one, this one, that'd be a higher energy. But it wouldn't be as high as energy if you eclipse two methyl groups. Okay. We've already talked about that. Except for the terminology. Right. What they're calling is torsional strain. Torsional strain is an increase in energy that arises in the eclipsed conformation. I'm not sure why they call it torsional strain, except that you all understand what torsion is. It's a twisting, right? So I've asked you this before, haven't anybody have physics? Okay. Okay, so you know what torque is. Torque is a force on a distance from a point of rotation. That's what we're talking about, torsion here. And used to be popular with some models of automobiles. Instead of springs, leaf springs or coil springs, they had torsion bars. So they had these metal bars that the movable end was grabbed on here with a rotate for the wheel to go up and down, and the other was fixed to the frame. And the composition of the bar was such that it could stand the torsional movement, but it would resist it. So it would give you that spring effect. That's torsion. So if you try to put a torque on this molecule to line up those things in eclipsed conformation, that's a torsional strain. Okay. So when this molecule, with a single bond, you do get rotation, but there's an energy barrier to the rotation because of the eclipsing effect. This torsional strain causes an energy barrier that has to be overcome in order to get to the other position. So you've got to have enough energy to do that. So theoretically, if you cool the molecule down enough, then it wouldn't have enough energy to get past that torsional strain. and it would be stuck in that position. So theoretically, you could keep it there in that position and fix that position. Now, if you wanted to have a certain type of chemical reaction going on, that might not be practical because the chemical reaction requires a certain amount of kinetic energy, the activation energy, in order to go. And if you cool it down to get the conformation you want, it might be too cold for the reaction to proceed. So there's trade-offs. But it does take a certain amount of energy. All right. Okay, so here we're the energy diagram is emphasizing a molecule that has a bromine on one carbon and a bromine on the other. So the highest energy eclipsed conformation is the one where the bromines are lined up and eclipsing one another. Bromine is a lot bigger atom than hydrogen. So they're going to have more interaction as they pass one another.
Wait. Why burning?
That's where it is on the periodic table.
I thought they, like fluorine was like one of the, was like the smallest.
Well, hydrogen's the smallest. Fluorine's got 9 protons. Right, so it's a lot bigger than hydrogen, and bromine's got 35 protons. It's a huge molecule. Plus, it's got let's see, 1, 2, 3, 4. It's got period 4, just like that. By comparison, it's huge. Right?
I think I'm thinking of with electronegativity.
Oh, no. We're talking about size. Yeah.
But I thought that was like, that kind of had something to do with electronegativity. That have anything to do with it.
Okay, going back to our periodic trends, right? Electronegativity increases from lower left to upper right. How about size? Size
I think CCM is a huge one, right?
Size increases as you go down and to the left.
Okay. That's CCM is huge, right?
Right, so cesium and barium would be monsters by comparison. Iodine would be bigger than bromine. Bromine's bigger than chlorine. Chlorine's bigger than fluorine.
All right, that's one.
And that,
Thinking of.
and that's simply due to the fact that you're adding levels to their electron structure. So you get those bromines eclipsing one another, and the energy barrier, the torsional barrier, increases to a massive amount. And you can see that in the diagram. Now you still get interferences of bromine with hydrogens. So you get a crest there where you have bromine and hydrogens eclipsing. But there's some more terms that are being introduced here. The anti-conformer puts those two bromines opposite one another. That's the lowest possible energy. The anti-conformation for a dibromo molecule. And I think they're borrowing from French here. Gauche. Has anybody had French?
Yes.
Okay. Gauche is to the right, correct? Now droite is to the left. So they're saying gauche is close, but not overlapping. I think in English we use gauche for something else. Like gauche is like gross, inappropriate or whatever. Do all dancers have to take French?
I think it's like bachelor's of arts, so I think you have to have either a language or like an arts.
Oh, okay. I remember when I went to college, you had to have a foreign language. There was no ifs, ands, or buts about it.
I like that process.
Yeah.
And now in college, we just have to have like electives.
Mhm.
We have to complete our electives, so we're like well-rounded students.
Yeah.
You can take Spanish. Like one of my friends, her minor was Arabic, and like she had to write a whole paper
Ooh,
But she speaks like fluent Spanish, like she's good.
languages. Yeah.
So she like a linguist or?
No, she just like in high school, she loved Spanish, like she took AP Spanish.
Hmm.
And then so she just did that in college and now she's in grad school and she's gonna be like a therapist. She's not really using it. But she could like use it if she wanted to help other people.
Yeah. Uh-huh. Yep. Okay, so the two new terms introduced in this graph are the gauche, the anti, where you have those, the torsional strain is the least amount. And you have the gauche arrangement where they're close, but they're not eclipsing. So that's also a trough. All right. Oh, okay. So there's a definition. The anti-conformation puts those bulky groups, as we're going to call them bulky groups, are 180 degrees apart. In terms of energy, that minimizes the torsional strain and the energy for the molecule in that conformation. When you put those bromines as far apart from each other as possible, which is 180 degrees of dihedral. But they can be closer, right? Rather than being eclipsed, their next closest possible arrangement puts them 60 degrees apart for the dihedral angle. And that's the gauche conformation.
So I guess the anti would be the ideal.
That would be the lowest energy, yes.
Okay.
Right. Right. That's the most stable conformer. And as far as percent, let's see, what would you say? Percent residence in a certain conformation, that would be the highest percentage, the anti, because molecules, atoms, chemical reactions tend toward the lowest possible energy. They tend towards stability. And this is the most stable, is the anti-conformation. Then there are intermediate stability, stable situations like the gauche. And that really, that depends on the amount of energy available to cause the rotation. Do you have enough energy to overcome the torsional strain? All right. Let's see. That looks like the same one we've been on already. Okay. You do get steric strain in the gauche conformation. That's undoubtedly, because you can see that from the energy diagram. But it's more stable than any of the eclipsed. It's an intermediate stability, right, in the gauche conformation. Any of the eclipsed conformations are going to be higher energy. But the highest energy is the one that eclipses the bulky groups. In this case, bromine. Okay. If we try to extend this conformational concept to larger molecules, this explains why we tend to draw large carbon chains, alkanes. This is an alkane, for instance. We tend to draw it in a zigzag. If we take that zigzag and turn it, just take one of the bonds and put that on axis and put the other. Let's see. Let's do that. If we have this 1, 2, 3, 4, 5, 6. We have this, that, 1, 2, 3, 4, 5, 6. And we have nothing but hydrogens on it. So this is what? Hexane, right? That's what we call normal hexane. If we take that one and we say, we look at this bond right here as on axis. Right, so we've identified this is one carbon, this big circle, and this is another carbon right here. So right down that axis is here. So what do we have sticking out of one side? Well, we have two hydrogens. Like, we always have two hydrogens there. There's only a single bond. And then we have this ethyl group. Right, so off of this one, we're going to have CH2, CH3. Big bulky group. Okay, so if we look at the back, we've turned it this way. So this is in front. Now what's in back? Well, if we continue to draw it as zigzag, we should put the ethyl group up here. This would be the lowest energy. And the hydrogen's down here. So that's if we're focused on that bond right there and these two carbons. Let's see, we have the right number of carbons. 1, 2, 3, 4, 5, 6.
Is there a reason we're focusing on that, big bond, you just chose that one?
No, I just picked it. Yeah, we could pick this one. And then we'd have a propyl group sticking out one side and a methyl group sticking out the other. Right. But the point is, that's why we tend to draw these conformations. The most stable conformation for an alkane is this zigzag structure, because of the minimal torsional strain that's afforded by that arrangement. All right, so each one of these would have hydrogens like that, like that. Okay. Now I didn't draw a dash wedge in there, but we could. Okay, let's see. 5 and 6 membered rings are the most common in nature. Okay, now we're gonna shift away from the Newman projection and talk about other types of conformers. Now that we have, we're gonna rely upon that concept of torsional strain on a bond of any kind, not just the torsional strain, but any kind of strain. We try to minimize that strain. And that's why most ring structures are either 5 or 6 members. So we see menthol on that first one on the left. Menthol is a 6-membered ring. That steroid molecule, androsterone, has 6 and 5-membered rings. 5-membered rings tend to introduce some strain, but not serious. It's not enough to it's not a deal breaker, in other words. Diamond is the perfect sp3 hybrid for carbon. Each one of those carbons is sp3 hybridized, and it's a tetrahedral structure. Now, if we focus on, I don't know if you can see, nah, my cursor's too small, but if you look at these 6 right here, right there, 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 and there, you see there's the 6-membered ring. We're going to look at that in a little more detail in a minute. Notice that the carbon in the top of that ring, so if we see, we have the carbon here, carbon and carbon, carbon like that. And each one of these carbons has 4 other carbons attached to it. That's diamond. Then you'll notice that this one is sort of pushed toward the back. So we could do like this. And this one is brought out to the front. Like that. So it kind of like that, and lifts like this. Ribose and deoxyribose We've seen those before. DNA and RNA. They're 5-membered rings. And in many respects, there's an advantage to the 5-membered ring because it tends not to flop around as much. This one, right, it could be like that and like this, but it could easily just flop like that, or it could trade places and go like this, like flop back and forth. So that tends to introduce different conformations. But the 5-membered rings tend not to do so much of that. All right, when we talk about ring strain, that's the amount of energy that's assigned to a ring. If we put those on an energy diagram, you'd see that you are actually storing energy in those strained bonds. So you have a combination of torsional strain and steric strain. And then on top of that, what's the ideal for sp3 hybridized carbon, the tetrahedral structure? What's the bond angle? The bond angle. If I had a, say
That's 109.5.
right. So here, the bond angle would be 109.5. That's ideal for a tetrahedral arrangement. Right. Anything less than that adds strain. So when you go, the cyclohexane is our 0 point. It gives us a perfect sp3 hybrid tetrahedral geometry at each one of those carbons. So there's no strain there whatsoever. If we take that down to a 5 carbon, then in order to do that, right, we have to one, two, three, four, five. We have to bend that angle. We have to decrease that angle, and that adds strain to the ring. So cyclopentane would have a ring strain compared to the cyclohexane. It would have a ring strain of 27 kilojoules per mole, and that's a significant amount. If we go down to cyclobutane, I mean, we go way up with only 4 carbons. Right? Because what's the bond angle now? 90 degrees. That's a long way from 109.5. Then you're increasing the ring strain in that, and cyclopropane is a little bit worse. I think the worst is going from cyclopentane to cyclopropane, cyclopentane to cyclobutane. You see the biggest jump, 27 to 110. And then you've already introduced so much strain now. I mean, if you can make a cyclopropane, then you've already got built in a whole lot of strain. You just a little bit more strain. Not that you can't make those molecules. I mean, they are real, they exist, but they're not very stable. And some of these molecules, if you want to use a compound that has that type of ring structure in it for a reaction, sometimes you have to make it on the spot and then continue with the reaction from there because they are so unstable. It's not like you can pull a jar off the shelf that's got cyclopropane in it. It's probably not going to be very stable for very long. Okay. Rank these from, let's see, let me get this thing out of the way. Least ring strain to greatest ring strain. The least ring strain is going to be the 6-membered ring, B. So B is going to be the least. And the next one is going to be what? The 5-membered, so that'd be A. And then the 4-membered would be D. And then the most ring strain is going to be C. And we've substituted a nitrogen in here for our carbon. But the concept of ring strain, again, is valid even if we do substitute. So BADC, yeah. All right. Okay. That the way I drew that one before with the dashes back and the wedges forward, that's known as the chair conformation. It looks like a lawn chair. That's why we call it that. And that's typical of the cyclohexane. That's the least strained position. Now, the bond strain, the angle of the bond strain is the same whether it's that way or whether we do a boat. It's called the boat. Chair versus boat. But when you do the boat, you introduce steric hindrance because now you brought those side groups up closer to one another and you're introducing some torsional strain. If we draw this in the Newman projection, then you just put two side by side. You have this one here, this one here. Okay. Then you're going to have in front, not like that, that, that. And then in behind, you've got this one, that. Yeah, these are connected. This is CH2, this is CH2. Right. And the rest are hydrogens. This is the Newman projection for the chair conformation. Notice that this one's up in front and that one's down in the back.
So why doesn't cyclohexane have no ring strain?
Oh, because the carbon is sp3 hybridized. So the ideal tetrahedral bond angle is 109.5. Now, because it's in a ring, we do have a little difference in the bond angle, but it's not much, like 109.5 versus 111. Did I answer your question?
Yeah.
Okay. Sometimes I lose track of where I'm at. And you know what? It might be instructive to build a cyclohexane. You need 6 carbons. You don't even have to put hydrogens on them yet. We just need 6 carbons. 1, 2, 3, 4, 5. I need one more. That one down and that one up. So if you got these two here at in the same plane as these two in the back, that places this one down and this one up. That's your chair conformation right there.
Yeah, I think it was-
Oh, you did a pentane.
Yeah.
That's fine. Cyclopentane. We're gonna need that one too. One, two, three, four. I need one more. There we go. Now for the cyclopentane, you're gonna have four of the carbons are in the same plane, and that puckers the fifth one, either down or up, depending on how you look at it. So envelope. That's an envelope conformation. Right? It looks like an open. You got the one flap of the envelope open. That's this carbon right here. And that's its most stable conformation. Part of the strain there is due to the fact that you have a partly eclipsed conformation. If you look at the Newman projection, it's a little hard to see without your hydrogens in there. But let's see, the way they have it set up, like this, that, like that. There we go. Like this. And if you're looking down the barrel of this one right here, that makes these two carbons right here partly eclipsed. And that adds some torsional strain in addition to bond strain. Because the bond angle, see, I mean, you can hold them up together. You can see the bond angles are smaller for this one than they are for the
Yeah.
6 carbon. Cyclobutane is worse. It's it's a puckered conformation. And the only way that the cyclobutane can exist is in eclipsed conformation. So that really, that to me explains why the energy strain on the cyclobutane went up so fast, so high, so quickly, right? It quadrupled because you've got that eclipsed conformation. Everything is eclipsed, and that's the only way that it can exist. Cyclopropane, it's pretty much everybody's eclipsed. There's no way out of it. You can't, the bond angles are 60 degrees.
So does that mean it's the lead, like it's very non-stable
Yes,
Okay.
it's very unstable,
Yeah.
correct.
or unstable?
Yep.
Okay.
Excuse me. Okay. I think what the author's trying to get at with this slide is these values that were presented for bond strain in these cyclic molecules is not just theoretical. You can calculate the values. And the way we calculate the values is to combust them. A combustion reaction, you take these cycloalkanes and you burn them in oxygen and you determine the heat, the enthalpy of combustion. So, let's see. And actually, in order to determine the strain, you've got to prorate it based upon a single carbon. So that's why if you have a CH2 with N under it, N means you have so many carbons in the ring. So if we have this CH2, and this one would be 6. Right, 6 carbons, 12 hydrogens. 2, 4, 6, 8, 10, 12. If we have this one, say like that would be CH2, 5. So that'd be 5 carbons and 10 hydrogens. 2, 4, 6, 8, 10. So once you determine the enthalpy for the reaction, you divide it by the number of carbons, and that gives you the ring strain per mole of carbon atoms. So here's an example. We've got the heat of combustion for cyclohexane is 3,690 kilojoules per mole, divided by 6, and that's 615 kilojoules per mole, right, for each one of the carbons. We do the same thing for cyclopentane, and we get 620.5 kilojoules per mole. If we set cyclohexane as 0, use that as our 0 point, then all we have to do is subtract 615 from 620, and that gives us 5.4 kilojoules per mole of carbons. Then for each carbon, we multiply it times 5, and that gives us the ring strain for the molecule. See how we're doing that? The difference between the two times 5 again gives you the total for the whole molecule. That's where that 27 kilojoules came from. Right? They didn't just pull it out of thin air. It's a calculated value. It's experimentally determined. Okay. Now, let's see. 1, 2, 3, 4, 5, 6. So they're using, for this example, now we need hydrogens attached. And if we put all our hydrogens in there, let's see. Where is it? Oh, I got another shoot. How'd I end up with these sp2 hybridized carbons? There we go. And this one's okay. So I need another bond. Right. And then swing this one around. Nope. Just throw them. Yep, run away. I know this is taking a lot of time, but these are concepts that are difficult to see on a flat sheet of paper. Okay, there's one. Right, this one's got positions for hydrogens. What we're trying to do here is is demonstrate the movement of the molecule from chair conformation to boat conformation and what it does to the positions of the hydrogens or the other attached groups. All right, well, there's another one. Let's get rid of that. I'm inclined to leave this one, once I get it built, just not take it apart. Okay. Yeah, there's another one. Rid of this one. Ah. Here we go.
So like this,
There you go. How do I keep ending up with these sp2 hybridized carbons? There. And one more. Okay. There we go. Now, there's my chair confirmation. Normally, I don't try to get these right down to the hilt. But since we're going to be moving them around, I think it's probably more stable if I be sure that everything's in place. Okay, chair confirmation. All right, one side up, one side down, like that. And then these two guys right in line with one another. Like that. That's my chair. Okay. We can assign names to these hydrogens in these positions. The ones that are pointing up away from the plane of the molecule are known as axials. So we have 1, 2, 3, 4 axials here. 1, 2, 3, 4 axials here. And we have equatorials that are roughly in the plane of the molecule. That's an equatorial. This is an equatorial. This is one. This is one. So we have 1, 2, 3, 4. There was more than that.
shouldn't there be 3 axials, 3 on the bottom and then 5 on the I don't know the next one. Equatorial,
Equatorial?
sorry.
Yeah.
So
So-
they should be, sorry.
No, you go ahead.
So
Oh,
they
yeah,
should be
3.
Alternating,
3 on the bottom, 3 on the top.
Yeah.
Yeah, you're right.
Okay.
Right. These are axials.
alternating like this.
Right. We're starting off from a chair confirmation. So these two bonds right here are lined up. But if we turn it slightly like that, now the plane of the molecule is like this.
You sit yours down at the table, so I can see how it's sitting. You have 3, yeah, I have 3 down here.
3 down, 3 up. Those are axials. And that means there should be 6 others, equatorials. 1, 2, 3, 4, 5, 6. Now they're not perfectly in line with the equator of the molecule, but they're very close. Now what happens when we flip the molecule from one chair to the other chair? We take this one down and this one up. Like that. What happens is the equatorials become axials and the axials become equatorials. Okay. That's all we've done. Let's see, put this one up, this one down. And let's see. Right, we have 3 up, 3 down, and 6 equatorial. And then when you flip the chair, you just convert one set of equatorials to axials and the other axials to equatorials. Now, during this flipping process, if we look at the energy involved, just like we did with the Newman projection and the rotation around the bonds, this flipping requires energy. So the chair is the most stable conformation of this molecule. The boat is an intermediate stability. There's the half chair where you line where you have this one flat like that, right? And only one of them pointing up is the least stable. Part of that problem is bond strain, torsional strain, and part of it is steric hindrance, because now you're getting more axial groups or atoms in that region, and they're interfering with one another. So the half chair is the least stable. The boat is unstable, but it's intermediate. It's more stable than the half chair. And the twist boat is you just take it and twist it like that. So it can go either way, that way or that way. The most stable is the chair. The least stable is the half chair. And intermediate is boat. And more stable than the boat is the twist boat. So when you get this boat conformation like that, what you're doing is, well, they're calling it, they've got names for everything. Organic chemists do that. Once you get this boat conformation, you get a flagpole interaction. In other words, these two guys are sticking up here and they're interfering with one another like that. That's one way to look at it. If you rotate the molecule, then you'll see that the boat conformation also puts many of the hydrogens in eclipsed conformation. Well, actually, not just the hydrogens, but the let's see, we do like this, that. Yep. We do like this. Okay, so now we're in a boat. Actually, my boat's upside down. That looks more like a boat. And we have these two in a Newman projection, these two right here. That, well, they've got it turned upside down too, so I'm going to turn it upside down like the picture. Like that. Now what we've got is these two carbon groups are eclipsed, and that adds torsional strain to that conformation. So what we're trying to do here is explain why the boat conformation is a higher energy than the chair. Okay. Shorthand notation. If we look at the chair conformation, let's put it back in the chair. Let's see. That, like that. This is down. This is up. There we go. Now, in the chair conformation, what does that say about representing this in the dash wedge? Well, we got to decide where we want the plane to be. So if we actually, that's not a good representation. Because look at the lines. The lines in that middle one, you would expect just a simple line for all those to be in the same plane. So we would have to tilt it like this. And it still wouldn't be right. Right? So I don't put much faith in that one. It's not consistent, is it? It's not consistent with the convention. Because straight lines are supposed to be in the plane of the board. And the wedges are supposed to be toward us, and the dashed are supposed to be away from us.
What part of it's not consistent?
If you look, let's see if I can get my cursor to show up. Where is it? Come on. There. If you look at these lines here, like that line, and then this line, and these lines, just straight, simple lines. In the past, we put those in the plane of the board. Right? If you try to put those in the plane of the board now, it doesn't work. Not with chair confirmation. Like, can we rotate it a certain way to get those lines to line up? Right? Because all those straight lines should be in the same plane of the board. Oops. Sorry. All right. So the dash wedge representation of this molecule, if we look at the one on the left, so the one with all the carbons and the hydrogens shown as spheres, you'll notice that over here, look at this one. That bond right there is not in the plane of the board. It's not in the plane of the board here. It can't be in the plane of the board there. So we have to throw that convention out the window if we want to use this arrangement. What we're saying is that 3 of those hydrogens on the bottom are axial. 3 of those hydrogens on the top with the plane lines are axial, and the others, 2 of the dashes, 2 of the wedges, and 2 of the straight lines, those are all equatorial. That's the only way this makes sense.
Sorry to interrupt, but
Yep.
I'm having a couple of family emergency, so I gotta go. Can I call you on Zoom and finish this?
Do you have an emergency?
Yeah, a family emergency. So is it okay if I get on Zoom and finish it?
Yeah, sure.
Okay. Thank you.
Okay. Yeah, I think we're going to chew up all our time today again. All right, so this shorthand notation, which is now deviating from what we were using in the past for individual carbons like methane and derivatives of methane. We have to throw that out the window. Now what we're saying is that when we draw the chair conformation, the way to draw the chair conformation is to look at parallels, right? If we have a parallel here, that's one bond. A parallel here, that's another bond. Then if we draw a parallel out like this, then the parallel on the other side of the molecule, it's got to be parallel to that one. And then, actually, I didn't draw that right. Let's do like this, that. Then this one has to be parallel with this one. And that gives you the illusion of the chair conformation. That's not drawn very well, actually. Something like that. That means if you only have hydrogens, now you're going to have axials here, here, and here. So these guys up, 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 and these guys down, 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 are all axials. And then the equatorials are going to be the other hydrogens at each one of these groups. There, there. Which direction do I want to go with this one? This, like that. 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 Like that. There's your equatorials. We're trying to use a shorthand notation, so to speak. And these are colored so that you can see the relationships. All right. So I already said that. Each of the carbon-carbon bonds is parallel to the one on the opposite side of the ring. That's the way we draw our chair conformation. All right. So I'm not telling you anything different. And we draw those attached lines the same length as the bonds that are in the carbons, so that they extend above and below and to the sides far enough so you can see the direction that they're pointing. In actuality, they'd be a lot shorter than that, especially if they were hydrogens. Okay. A monosubstituted cyclohexane. What does that look like? Monosubstituted just means that you remove one of the hydrogens and put something else there. In this case, we're substituting a methyl group. Now, if we put a methyl group in, let's see, I'm gonna do like this. Okay, I got my model, and this is the way it looks on the screen, like that. Only now this hydrogen, this axial hydrogen, we're going to substitute a methyl group. And I probably should put all the hydrogens in here because that will emphasize the steric nature of any problem conformations that we encounter. And I got to use the right carbon. These sp2 hybridized carbons keep slipping in on me. There we go. Okay. All right. So if I put that methyl group in here in a chair conformation, that methyl group is now axial. Okay. Notice that even if it spins around like this, you still got lots of steric interference here in the axial position. But if we flip it, if we do that flip, now it becomes equatorial. And it's got a whole lot more space out there. Yeah. So in this case, this monosubstituted cyclohexane is more stable with the substituted group in the axial position. I mean, equatorial position. Okay. Here we go. Like that. And we're still talking about isomers, right? This is an isomer of the other one. It's a conformational isomer. And right, that slide just tells you what I told you. Right, bulky groups like that prefer equatorial conformations. Now, how would that look with a Newman projection? If we put it back in the axial position, like that, and we looked, let's see, we looked, here we go. We looked down these two. That puts this methyl group up here. And the I forgot my terminology now. The angle. What do we call that angle? Is 60 degrees. I should go back and look. Dihedral. The dihedral angle. Now, in that conformation is only 60 degrees. Whereas if we flip it like this and put it in the equatorial position, now the dihedral angle.
Does it get ever to 180? Or does it get close to 180? It doesn't seem like it would get to
No.
complete 180.
No.
It gets close to it.
And it depends on which one you're comparing it to. You tend, when we're talking about dihedral angles and these cyclo compounds, you tend to focus upon the dihedral angle that was given the most trouble. So we're looking at dihedral angle between this one and that one, and these two and that one. And we find that in this conformation, the dihedral angle now is, it looks like it's almost 90 degrees. And you're seeing flagpole interactions when it's in the axial position. That's the one on the left. Whereas if you flip it to the and we're numbering our carbons too. If we number the number one carbon on the ring as the one having the substitution, which we should do, then the interactions between this one and that one would be called a 1-3. Right, 1, 2, 3, or go with this direction, 1, 2, 3. So we just call it a 1-3 rather than a 1-3-5. It's a 1-3 because if you're talking about interaction here, it's a 1-3. Interaction here, it's a 1-3. But if we put it in the equatorial position, we don't get that interaction. Okay. So if we have a a substituted cyclohexane. And these are the different groups that you can substitute for them. Either the hydroxyl, the amines, the methyl groups, ethyl. That next to the bottom one is a propyl. It's a propyl group. Actually, the way it's written, it should be substituted as a, says put it out this way. There's a carbon like that, like that. So that's the propyl group, the next one to the bottom. Right, 3 carbons, 1, 2, 3. And the attachment point is on the number 2 carbon. That's why we put the CH3 in parentheses with a subscript 2. And the bottom one is what's known as a tertiary butyl. So in that case, we have 4 carbons. So we have 1, 2, 3. Yeah. This one is going to be three carbons attached to that carbon. That's known as a tertiary butyl. Tertiary because that carbon is attached to 4 other carbons. Or 3 carbons. 1, 2, 3. Primary, secondary, tertiary. So that's tertiary butyl. Now, it's actually not a tertiary, but a quaternary because that carbon is attached to this one and those 3.
And
But
is
the
that why
side
we're
group
calling
is,
it rather than purple.
yes. Well, that's another one of those cases where it's kind of grandfathered in.
We had a homework question that I was just looking at.
Okay.
And it was talking about the 1,3 diaxial interaction.
Uh-huh.
And it's asking about their experiencing the largest. So I don't think I have this completely set up right, but
Experiencing the largest what?
1,3 diaxial.
Oh.
So I'm thinking the largest distance, or is it not necessarily that?
No, not the largest distance. The largest steric interaction. That would increase the energy of the molecule. So it'd have to be an axial position. Right? Oh, you've got 2 methyl groups, right?
Right here.
Does it tell you where the methyl groups have to be?
No, so I'm just clicking on whichever ones are experiencing the largest.
Oh, it's given to you that way.
Yes.
Okay. So which would be the largest interaction? Actually, those 2 pointed down.
These 2, these.
Yeah, those 2, that one. And that one. Or just allow you to identify just, yeah. There you go. Those 2.
And those are because,
They're both. And they're both axial. So
like this, they look like this.
they're in each other's neighborhood.
It looks like this.
Yep. And there will be another one over on this one. Let's see, 1, 2.
And that's all we were talking about. It's more stable because in that corner position, because
Yes.
it has more room to do its stuff.
Right.
Rather than if it's up here, it gets all jumbled.
Yeah, and especially if you've got another methyl group in an axial position. That would really be a hindrance. Okay. So what we're trying to let's see. Okay. So we've got 2 columns here of our cyclohexane, substituted cyclohexane in a boat conformation. One in which the substituted group is in the axial position and one in which it's in the equatorial position. If the substitution is not there, if they're hydrogen in that position, then they're equally as likely. Right. The percent in the actual position, the equatorial position is going to be the same. But if you introduce a hydroxyl group there, you're going to instantly go from 50-50 to 1981. So it's going to prefer the equatorial position. NH2 being a bigger group is going to be even further. Methyl being a little bit larger than that is going to be. So we're increasing, as we increase the size, the bulkiness of the side of the substituted group, we increase the percentage in the equatorial position. And that has an impact on how the reaction proceeds. In other words, if the molecule tends to be in an equatorial position 99% of the time, then any reactant that comes in there and attacks the molecule is going to be seeing that predominantly that conformation. And that tells you something about what you can expect as a product. All right. Let's see. What is this? Just closing remarks. Oh, no, we're going to another projection, the Haworth projection. All right. So the chair flip does what? I got to get that out of the way. The chair flip doesn't switch a substituent from one side of the plane to the other. It goes from axial to equatorial or equatorial to axial. That's all the chair flip does. If there's a cis-trans relationship between any pair of substituents, now, yeah, let me finish the statement. The cyclohexane ring is independent of the chair conformation the species is in. So if there's a cis-trans relationship between any pair of substituents, that doesn't make any sense to me. It's either cis or it's trans. What we mean by cis is they're on the same side of the molecule, like those two methyl groups that we were just looking at. Those two methyl groups that were the most interfering with each other were cis to one another. They're on the same side of the molecule. Whereas if you have one that's hanging out here and the other one's like this, they're trans. So substituents that are cis to each other on a ring remain cis after a chair flip, and those that are trans. All right. I'm not too happy with information that's left out. We talked about cis and trans with respect to double bonds. So what I'm trying to do is to translate that concept into what it looks like on a ring.
This would be the easiest way for me to visualize it. You can do it like this. Can you do it?
Yeah, okay. Yeah, let's see if we can do that.
Understand the wedge and dashed line on the board kind of thing, but I mean, could it be as simple as these two are replaced with two colors versus this one's trans?
Let's say, let's take that example where you had, let's see, this one like that. Let's put it down like this. And then you had another one over here, right? Let's see. Nope. Here we go. Let's put this one here and then fill in the hydrogens. So we're going to put two methyl groups here on this molecule. So it's a disubstituted with methyls. All right. And if we, let's see, the chair conformation would be like that, like that. So would we consider that to be trans? Are they both,
I would say it was cis because they're in the same, it seems like they're kind of in the same. place.
if they're on the same, right,
Now, if one of them was shooting up and one of them was shooting down. I would consider it trans.
that's trans. Cis would be on the same side. Right? But these are equatorial. So what if the molecule flips? This. Now they're still on the same side. Right? They're actually this is cis. Right? That like that.
Do you hold your model like this for some? So you're at 1 and 3.
Yeah, I'm at a 1 and 3. Trying to figure out what they mean by cis and trans. Now, I think what we're getting at here is we're moving toward the Haworth projection, which is a simpler representation of the ring structure. Hold on a second. Maybe there's a more complete explanation of this in the textbook. What do they mean by cis and trans when we're talking about a ring structure? Correct? Because that's what's throwing me. That's the end of the chapter. Let's back up. There's the Haworth projection. Cis-trans isomers. Okay. With di-substituted cyclohexanes, we have to take into account the relationship of each substituent to the plane of the ring. Are they on the same side of the ring, cis to each other? Or are they opposite sides? A chair flip. Okay. Same side of the ring or opposite sides of the ring. So that's basically what we were saying before. All right, if we do, let's see, I've got it in a 1-3 position. And I'm trying to do a chair conformation. Right, with these guys lined up. All right. So are they on the same side of the ring? Well, if they're equatorial, there's no difference. Now, if we do a chair flip, put this one down and this one up, they're still on the same side. They were equatorial, now they're both axial. So what we're saying is the chair flip, these are cis. They're on the same side of the ring. If we do a chair flip, it doesn't change their conformation. What if I put them, it might be easier to see if we put them in carbons right next to each other. Yeah, I think that would be easier to see. So I'm going to put them on the 1, 2. All right. So let me get the chair.
Are you putting them on?
Hold on a second. I think I'm going to put them on opposite first. So there's my chair conformation. And there's my methyl group. I'm going to put this methyl group opposite. So that's trans. Right? That's trans. Okay. Now, what if we do a chair flip? Right. This one's up and this one's down. With this one up and this one down. Now they're both equatorial. They were both axial before, now they're both equatorial. So I think what they're trying to say is just like when we were talking about equatorial becomes a axial, and axial becomes equatorial, cis becomes trans, and trans becomes cis. But the relationship, now they're not saying that. The chair flip doesn't affect that. All right. This is confusing. And I know it must be confusing you because it's confusing me. A chair flip does not switch a substituent from one side. Let's look at an example. All right. You know what? This only makes sense. It's virtually impossible for me to see this as cis trans with this type of modeling. When you use the Haworth projection, which actually takes the ring like this, and it tilts it. It tilts it like this, which means now we say these are in, this is in the back, and this is in the front. So we're actually tilted at some like this. Now, when we have a substituent here, say we're using our methyls, that's cis. And this is trans. Now it makes more sense. I mean, it looks right with a Haworth projection. Now, how does that look? Look in figure, well, you don't have your books up. In figure 430, let me go to the next. There we go. So that's figure 429 in your book. And the relationship between the dash wedge and the Haworth projection is shown there. If we do the dash wedge, the X and the Y are coming out at us, both wedges. If we do the dash and then a wedge for the X and Y, then we're saying that one's pointing back and one's coming out. Those would be trans. And then when we rotate it around like this, that puts the X on the bottom and the Y on the top. I guess what they're saying is that's the advantage to the Haworth projection. And it's most often used in cyclohexane molecules or six-membered rings. Doesn't have to be, but I've seen it most often in six-membered rings. Now, if we do the Haworth projection for cis 1,3-dimethyl cyclohexane, which is there on the left, and then we translate that into a chair conformation, that's saying that those cis methyl groups are now actually equatorial. Whereas with a trans, one is equatorial and the other is axial. And if you flip it, you still get an axial and equatorial. Whereas with a chair flip, now you go from 2 equatorials to 2 axials. Okay, I was looking at it the wrong way. Trying to do this molecule. If they're both equatorial, that's cis. If they're both axial, that's cis. Okay. Are you calling up the book?
Yeah, I'm trying to see what we have, but. Kind of in our homework, it'll show, I see section 610.
Oh,
or
okay. Yeah.
it'll do something like that, but sometimes mine's fine,
It doesn't always tell you to go.
or mine won't give me access.
Oh. Maybe it only does that when you're once you finish the problem,
Okay.
which is not very helpful. Okay, so here's the takeaway. What they mean by cis and trans is cis is they're either both substituents are equatorial or both substituents are axial. And the chair flip keeps them, one of those others, one or the other. For the trans situation, one is equatorial and one is axial. And the chair flip keeps that relationship. So when you draw the Haworth projection, it's easier to see the cis relationship because they're both on the same side of the molecule. And if you draw the Haworth one down, that's a trans situation. Is this making any sense? So they're trying to show you in the model what it looks like. Right? If one's axial and one's equatorial in the drawing, then you have a trans situation. And the chair flip maintains that relationship. Okay. So let's leave that one behind us and try to get done before we run out of time. Because we still got chapter 5 to go. These constitutional isomers, and it's nice of them to tell you that they're also called structural isomers, have the same molecular formula but different connectivity. We did that already. So cyclobutane and but-1-ene are the same molecular formulas, but they're different connectivity, right? Obviously, one's cyclo and one's not. And then the 2 molecules below have the same formula, but they have different connectivities. Right? So they would have a different name. Those are isomers. Those are structural isomers, constitutional isomers. Those 2 terms are synonymous. You think you'd have any trouble telling the difference between a constitutional isomer and any others? Those should be the easiest to figure out, especially if you got a straight chain and a ring structure, right? That's obvious. Or if the branch is different and you look for the parent chain and the parent chain's 1 and 1 and different in the other one, then you got constitutional isomers, structural isomers. And that's what they're saying here. Are these molecules constitutional isomers? At first glance, it looks like they're not. I mean, they are constitutional isomers. But if you count the longest carbon chain, which is 6 carbons, and say, where are the methyl groups now? They're on the same carbons. So these are not constitutional isomers. Right? They're just drawn differently.
They're not.
No, they're not. If we drew, let's see, let's draw the 6, 1, 2, 3, 4, 5, 6, and they put it on 2 and 4. Methyl group here, methyl group there. And the other one, we're drawing 2, 3, 4, 5. And we're putting, let's say I put that too close. We move it over here. 3, 4, 5. And then we put that one like that. The longest chain here is 6, right? 1, 2, 3, 4, 5, 6. The longest chain here is 1, 2, 3, 4, 5, 6. Oops, I left this one. Where are the methyl groups? Methyl groups here are on 2 and 4. Methyl groups here are on 2 and 4. It's the same molecule. We just drew it differently.
Now, what about the fact that that's an ethyl group? Is that's not ethyl, I guess?
No, because that's part of the parent chain.
Oh, right.
Yeah. The side chains are these 2 methyls, methyl, 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 and they're both, yeah, they're on the 2s and 4s. Okay, saturated molecules, I think I mentioned this earlier. Saturated molecules have no double bonds, have no pi bonds anywhere in them. They're completely saturated. They've got all the hydrogens they can hold, in other words. And they have no rings. Rings tend to reduce the number of hydrogens that you can have. Why? Because in a ring structure, you've got secondary carbons. All your carbons are secondary. Right? In an alkane, they're primaries unless they have side groups. And they have fewer hydrogens are available in a ring structure. Right? If we drew, let's take it simple. Let's say, well, let's do the 6. Right? There we have. So how many hydrogens do you have here? We got 3 here, right? You got 2 there, 2 there, 2 there, 2 there, and 3 there. So it's C6H14. 2, 4, 6, 8 plus 6 is 14. All right. If you close that into a ring, right? We've still got 6 carbons, but how many hydrogens can you have? Well, you can have 2 here, 2 here, 2 here, 2 there, 2 there, 2 there. 2, 4, 6, 8, 10. That's C6H10. Right? No, 12. I miscounted. 2, 4, 6, 8, 10, 12. There we go. So you're missing 2 hydrogens. That process of going from alkane to cyclo removes hydrogens. It partially unsaturates. This would be complete saturation. This will be partially unsaturated. You can get that effect with ring structures. You can get that effect with pi bonds. Right? So if we stuck a pi bond in here, right, that would take 2 hydrogens away. This would have the same formula as this one. Okay. Now, why am I talking about that? Because we're going to calculate what's called the index of hydrogen deficiency, IHD. Index of hydrogen deficiency. I think they left out a word. Index of hydrogen deficiency. That's what the D stands for. What it is, well, it's used. Well, let me not jump the gun. It's half the number of hydrogens that are missing from the molecule for the saturated molecule. Right. So if we were to say, what's the IHD for this one? Well, how many hydrogens is it missing? Right. Well, it should have been 14 here, right? 14. So it's missing 2. Divided by 2 is 1. So the IHD for this one equals 1. Okay. If you have a double bond, you get the same effect as you did down here. The double bond reduces, changes the index from, this would have an index of 0 because it's got all the hydrogens it needs. It's not deficient in any way. So if we put a double bond in there, that removes 2 hydrogens. Or divided by 2 is an index of 1. So if we did this, the IHD equals 1. Right? If we did that, index would be 2. Okay, that's the way you calculate the index. If we had a triple bond in here, like this, that would be 3. So you can look at it that way. You can calculate it, just bulldog it, or you can learn these rules. Each double bond contributes 1 to a molecule's IHD. Each triple bond contributes 2. Each ring contributes 1. So if it's like this, if you have a benzene ring, now it's useful, rather than put that circle in there, to actually draw the double bonds into it. So the IHD now is going to be 1 for the ring, 1 for each of the double bonds. So benzene has an IHD of 4. Okay. And there are other examples there. It's probably quicker. Just learn the rules. So ethene has an IHD of 1. Ethine has an IHD of 2. Let's see, if we take the ethanol and we make a ring out of the oxygen and the 2 carbons, right? If we have the carbon and the carbon and then oxygen over here, we bring that oxygen around here, and instead do like that. Now you make a ring structure, right? And you've got 1 ring where you didn't have one before. Now the IHD is 1 because we added a ring. How about naphthalene? What's the IHD for naphthalene? Naphthalene, this is known as a fused ring structure. Right, so we've got this one, this one, this one, and then this one again, this one. This is a fused ring structure. When 2 rings share 2 carbons, they're said to be fused together. If they only share 1 carbon, then they're linked. So we've got 2 rings, right? And how many double bonds do we have? 1, 2, 3, 4, 5. So that IHD is 7. Index of hydrogen deficiency. 2 rings. Yep. Let's see. Saturated hydrocarbon with N carbons has an IHD of 0. Chemical formula is, all right, this is any alkane. You can calculate the number of hydrogens of an alkane if you know what's this value right here. Say this is 5. Then this one is going to be +1 times 2 equals 12. That's the way I do it. The way they do it is to say 2 times this value, then +2. So 2 times 5 is 10, +2 is 12. But I add 1 first and say 2 times that. It works the same way. All right. Heteroatoms in a saturated molecule. If you add a hydrogen, let's see, are they saying add or substitute? They're saying add. So if we add a hydrogen, add an oxygen, what does that do to the number of hydrogens? It doesn't change the number of hydrogens at all. Why? Because if you go out here to the end of the molecule and you start off like that, then you add an oxygen and a hydrogen, then you got the same number of hydrogens. So you didn't change the number of hydrogens. Right? When you add an alcohol group on the end of a molecule. But if you add a nitrogen, nitrogen wants to have 2 hydrogens. So now we've increased the hydrogen number by 1. If you add a halogen, if you substitute a halogen, it only wants 1 bond. So you've removed the hydrogen and decreased the number of hydrogens by 1 by adding a halogen. So we focus our attention on nitrogens and halogens. Oxygens we can ignore. If we're calculating the number of hydrogens in a saturated molecule, we've got the 2N plus 2, and then we have if we got an oxygen on there, you can forget it. It doesn't matter. If you have a nitrogen, we say 2 times the nitrogens, right? 2 times the number of nitrogen atoms minus the number of halogens. And that gives us total hydrogens. Okay, so the reason we introduced this concept is to help us calculate this IHD again. So if we have this molecule, C7H8, let's see, does that have a ring in it? It doesn't say it has a ring. So we can't assume that it has a ring. H8, NO2Cl3, NO2Cl3. So how many hydrogens does it have to start with? Well, if it's aliphatic, then it would be 16. 16 hydrogens. Right? 16 hydrogens. All right. We've got 1 nitrogen, which will increase that value. Let's see. Right, 16. And then we've got 3 halogens, which will decrease it. All right, so 16 plus 1 is 17, minus 3 is 14, right? 14 hydrogens. So how many hydrogens are missing? Well, if we started with 16, right? Hold on a second. The given molecular formula has 8 hydrogen atoms, which is 6 fewer than 14. Oh, that's right. Well, that's 14. Right? Yeah, that's 14. The number of hydrogen atoms in the saturated molecule should be 14. So these are the numbers for the saturated. But how many do we actually have? We have 8. So 14 minus 8 equals 6. So we're deficient by 6 divided by 2 equals 3. So that's the IHD for this molecule. Okay, did I lose you? What we're saying is, this is the given formula. But if we're starting from an alkane, a saturated molecule, how many hydrogens should we have? We should have 16 with a saturated molecule. All right. But we have nitrogen, which adds 1. And we have 3 halogens, which is minus 3. So the saturated molecule would have 14 hydrogens. But we only have 8 in the formula. So we're deficient by how many? We're deficient by 6. And the IHD is the number of deficient hydrogens divided by 2. So that's how we ended up with 3 as our IHD. Okay. Okay. So where we're headed with this is we're trying to develop a technique for drawing all possible isomers for a given formula. And determining the IHD helps us do that, because the IHD may be due to these added groups or added atoms. It may be due to pi bonds. It may be due to ring structures. And those all go into the mix for proposing a set of isomers for a given formula. They could be just 3 or 4, right? Or they could be a couple of dozen, depending on the size of the molecule. So what you do is, the first thing you do is determine the IHD. If you're given a formula, find out what the IHD is. And that's what we just did for this one. Once you know the IHD, that tells you that you have possible mixes. If you have a backbone of 7 carbons and you put them aliphatic, then you can introduce these components, right? The nitro, and the chlorides. And then you can introduce double bonds and triple bonds, depending on the size of this one. Right? This would be equal to what? One double bond would be 1. 2 double bonds would be 2. 3 double bonds would be 3. So we could put 3 double bonds in there. Or we could put a double bond and a triple bond, and that would add up to 3. Okay. So you want to draw the backbone and leave out the double bonds, triple bonds, and halogens. You add those later. Then you propose rings. But you can't put a number of rings in there that exceeds the IHD computed in the first step. Right, so how many rings could you possibly have? You could possibly have 3 rings. Right. 1 for each ring. Then for each, it's like a tree. You could propose several of them, and then you could add double and triple bonds afterwards. And then the halogens come last. I think it would work best if we have examples. So let's try this example. Let's see, we've got 4 carbon backbone. 1, 2, 3, 4, right? Then we have a fluorine on this end, and we have a fluorine on this end, right? And let's see, that's it. We have the rest is hydrogens. So the formula is C4H8F2. C4H8F2. So what would the aliphatic number of hydrogens be? Be 10, wouldn't it? 4 plus 1 times 2 is 10. So 10 hydrogens. And we've got 2 fluorines. So we're subtracted 1 for each one. Minus 2 equals 8. Well, 8 is the number of hydrogens we have. So our IHD is 0. Okay. This is a saturated molecule. So what are the possible isomers now? Well, now that we know that we don't have any rings and we don't have any pi bonds in here, we can stick to the saturated situation. This is one possibility. Okay. What's another possibility? To put 4 carbons in there. Well, suppose we take the backbone, right? This 1, 2, 3, 4. Let's say we take one of those carbons and put it on, we can't put it on the end, right? It's already on the end, right? We'd have to put it on this one right here. Right? So that'd be 1, 2, 3, 4, 1, 2, 3, 4, 4 carbons. Right? No double bonds, no triple bonds. We've got halogens. Well, no halogens so far, like this. Right, we're going to remove those and those now. So these are the 2 backbones, possible backbones. This is the only possible backbones. And no rings. Right? So where can we put the fluorines? Well, now we're gonna branch. We got this one and that one. What can we do with this one to position our fluorines? Well, we can put a fluorine on this one. Oops. Sorry. 1, 2, 3, 4. Okay. 1, 2, 3, 4.
Why is that one not labeled with the 4th one? There's 1, 2, 3, 4, and the other one.
Oh, that one doesn't have a 4
Right.
because this is the backbone.
Yeah.
That's the backbone. Yeah. So where do we put the fluorines? Well, we can put a fluorine on the end. Right. Then where can the other fluorine go? Well, it can go here. Right. Like that. 1, 2 difluoro. What if we put 1, 3? That would be different, wouldn't it? Fluorine here and a fluorine here. That's 1, 2, 3, 4. So 1, 2 difluoro or 1, 3 difluoro. How about 1, 4 difluoro? So we put a fluorine there and we put a fluorine here. 1, 2. There we go. So are those all the possible constitutional isomers? Or if we do this, is this different than the rest of them? I think so. Is this different? What if we numbered the other direction? It'd be 2, 2, 4 instead of 1, 3. So 1, 3 is better. So I think those three are possibles. How about no double or triple bonds because the IHD equals 0. That's true. Add 2 fluorines. Molecule from step 2. What about this one? Where could the fluorines go on this one?
Why couldn't it go on that methyl coming out of the top? Because it
would look exactly like this one.
Okay, that makes sense.
Yeah, if this fluorine here and the second fluorine was out of this one, that's possible. What if we did this one with a fluorine here, like 1, 2, 3, and a fluorine here? Would that be different? I think so. So, oh, we left one out. What if we did two fluorines off the same one? That would work. And then we did this one, right? That's H. I would be that one. And this one. And you may end up writing what you think are isomers, but when you compare them to the others, usually the best way to do that is either rotate or flip and see if it looks like any of the others. Let's see. We could put C4H8. C4H8. 2. We could do another one. 2, 4. And we could put both of them on the number 2. That would work. Or we could put 2, 3. Do we have 2, 3? We don't have 2, 3 in there yet. Right. One here, one here. Like that. So these 1, 2, 3, 4, 5, 6. We have 6 possible. Yeah, 6 possible isomers of the butane derivative. How about the propane derivative? Well, the propane derivative could have, we could have both of them on one end. A fluorine here and a fluorine here. Right. Then we could have a fluorine there and a fluorine here, which we do. Right, that's P. Then we could have fluorine on either end. And that's it. That's all. We can only have 3. So we decided we could have 1, 2, 3, 4, 5, 6 of the butane derivative, and we could only have 3 of the propane derivative. All right, here comes another one. Let's see, we've got C3H6O. I'll put it up here. C3H6O. All right, so the IHD for this one, we're going to start with 3 plus 1 times 2 equals 8. So we're expecting 8, and we've got an oxygen there which has no impact on the IHD. So we got 6, but we want 8. So our deficiency is 2 divided by 2 is 1. Our IHD is 1. So that means we can have one ring structure. So what are the possible rings? Well, we've only got 3 carbons. So you could have a cyclopropane, right? Or you could have a heterocyclic with an oxygen in that cycle. Or you can have all 3 carbons with the oxygen in there with them. Those are the possible ring structures. Okay. With three carbons, you can either have 1, 2, 3 like that. Actually, that's the only way you can do it. That's the only backbone you can have with 3 aliphatics. And then position the oxygens. So the oxygen could be like this, or the oxygen could be like actually, the oxygen could be here. You put the carbon out there. It's 1, 2, 3, 1, 2, 3 carbons, and the other one we could put. We could branch it and put the oxygen here. So the alcohol can connect to the 1 carbon or the 2 carbon. Or we can make an ether out of it. 1, 2, 3. So those are the possibilities for no rings. All right, now that we've got possible backbones, then we've got to say, all right, how are we going to make we've taken care of this one IHD in that ring structure for those. But for this one, the ring structure, the aliphatic structure, we can introduce double bonds. One double bond will take care of each one. So if we have this possibility here, right, and we take this one and we put a double bond someplace, where are we going to put the double bond? Well, you can put a double bond here, right? You can put a double bond here, right? Or you can put a double bond there. Right? Let's see. Oh, and then this one. How can we deal with that one? So that's this group. And how about this one? Where can we put a double bond here? Well, we can take that one. That we can put a double bond here. Right? Let's see. Where else could we put a double bond? We can't. There are no other double bonds possible. Why? Because oxygen can only have 2 bonds. If you've got a carbon on that side and a carbon on this side, then you can't put a double bond here. That would be 3 bonds to that oxygen. That would exceed the octet. Can't put a double bond on that side. So that's stuck. For this one, that's the only double bond you can put in there. How about this one? All right. So this one, we could put a double bond there. Let's see. Oh, Sure. What if we tried to put a double bond here? Just rotate it, right, that's a single bond, just rotate it over, it looks exactly like that one. Like. So that's nothing new. Or we can do a double bond to that oxygen. So we've got this one, this one, this one, this one possible, got this one possible, got this one possible. Now we got to go to the ring structures. Oh, I thought we were going to go to the ring. Oh, wait a minute. That's it, right? This would have to be. Oh, I left out the OH. There. Now, does this account for the formula? C3H6O. Right, each one has an O. Each one has 3 carbons. 1, 2, oops, that one's missing 1. There. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, each has 3 carbons. How many hydrogens do we have? We got 1 hydrogen there, that's all you can have. We got 3 bonds here, so you can have another hydrogen there. You can have 2 here. Right, 4 for each carbon. You got 2. 1, 2, 3, 4, 5, 6. Okay, that's good. This one can have 3. This one can have 1. This one can have 2. 1, 2, 3, 6. That's good. This one can have 2, 2, 2. That's 6. Okay. So that's all we can have there. The reason we can't do anything else to them is because we've already used up our IHD with the ring structures. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 possible constitutional isomers for that formula. Takes practice. I need to practice too. All right. Okay, we did that already. Constitutional isomers, amino acids, and monosaccharides. All right. What's an amino acid?
Building block of a protein.
Correct. We want to look at it from a formula standpoint. Why do we call it an amino acid? Well, let's see. We've got a carbon, which is called the alpha carbon. That's our alpha carbon. And out of that carbon, we attach things to it. One thing we attach to it is an amine group. That's the amino part of the name. And the other part we attach to it is a carboxylic acid. Okay. Now, we also attach to it, that carbon only has 2 things on it now, it needs 4. So we attach a hydrogen to it. And then over here, we attach one of any of several different things. These R groups determine the character of that individual amino acid. Right? If we make that R and H, hydrogen, acid, amine, this molecule is glycine, the simplest amino acid. If we change that to a methyl group, right, or make it a methyl group, right, so the carbon would be bound to this carbon, that's alanine. There are lots of amino acids, but when you talk about essential amino acids for our metabolism, there are about 20. Right. Now, notice in this molecule, let me write it the way they've got it written. Their structure. So there's your alpha carbon. There's your amine group. There's your there you go. And we don't draw the hydrogen in. But we do have a side group here, this R group, which is like that. Oops, sorry. There we go. 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. That's leucine. And this is the R group. Okay. Isoleucine is 1, 2, 3, still 4. But instead of being attached, 1, 2, 3, 4. Isoleucine. Okay. So this one, the R group is like that. For isoleucine, the R group is 1, 2, 3, 4, and it's attached here to the molecule. The different attaching points. Here it's attached to this, let's see, 1, 2, 3, this methyl group off the second carbon. And this one is attached directly to the second group, rather than being attached to this methyl group here. Those are isomers, constitutional isomers. Leucine versus isoleucine. Now, I'm not sure why they call that one iso and they don't call this one iso. Because that's a straight chain and this is an iso. So they got it backwards in my world. But we have to go with what's given. Okay, so what does it look like for sugars? Well, the sugars are funny. They can exist in an open structure, an aliphatic structure, or they can, the head can grab onto the tail and make a ring structure. That's what we're showing here with the double barbed arrow, right? The left-hand side is the aliphatic side and the right-hand side is the ring structure, and they can open and close, right? If they're out, if the molecule is separate, like this, it's not combined with anything else, then it's free to open and close its ring. This, let's see. Ribose is on the left, glucose is on the right. Okay, I usually draw glucose using a Haworth projection. Okay. So this is going to be that looking out, and this is going to be, no, sorry. This is going to be the oxygen. And I've got an OH group down, an OH group up, an OH group down. And then this one is a CH2OH. So that would be wait, this is, okay. Okay. The glucose, and there are a lot of isomers of 6 carbon sugars, right? You can position these hydroxyls different ways and make lots of different 6-membered rings or 6 carbon sugars. These are called hexoses. Or very often they prefer to say aldo hexose. The reason is that the end of the molecule, before it gets into the ring structure, is an aldehyde. It has that carbonyl group on the end. So this one would be 1, 2, 3, 4, 5, 6 carbon. And then it would have that on the end. That makes it an aldose. If it has, let's see, I think all of them have hydroxyls. Now, drawing it this way, you can't tell that this is related to that because I didn't show you the whether it's pointing in or out on those hydroxyls, because each one of these has a hydrogen on it also, and it could be going this way, it could be going that way. So the way they've drawn it there, this one is, these are dashed like that. And this one is wedge. And that one doesn't have a direction because it's on this single bond and it just spins. Right, so it could have a conformational arrangement, but constitutionally it's neither here nor there. So this example is glucose. It's an aldohexose. But what happens is this end reaches around and reacts with this end over here. And that's where this oxygen bond comes in. So what happens when you combine this carbon and connect it to that oxygen? Let's see. Still need 6 carbons. All right, so this one, actually, this one right here is that one. Right, it sticks up. So the reaction is between this one and this one here. So this one grabs hold of that carbon and makes a 1, 2, 3, 4, 5, 6-membered ring. And that hydroxyl now is this one. And it can open and close just at will. And you can use the same logic for the ribose or the pentoses. All right. So what's the difference between ribose and ribulose? The location of the carbonyl group. The ribose is an aldose, whereas the ribulose is a ketose. Aldopentose versus in this case, a ketopentose. So you just move this one over here and put the hydroxyl over there. Yeah. So if you take glucose, if you take the straight chain glucose, which is in the second tier, and you move that carbonyl group over 1 carbon, then now the reaction is between the hydroxyl on the next to the last carbon and that carbonyl. That gives you a 5-membered ring, but you still have 6 carbons. So the ketohexose of isomer of glucose gives you fructose. Right? Fructose is derived from fruit, right? Fruit sugar. All right. So let's leave those for now and talk about fatty acids. Fatty acids are just that. They're acids. They have the carboxylic acid on the end. And then you can go however many carbons you want. And if it's aliphatic, this is unsaturated fatty acid. If you introduce a double bond in here, then you have an unsaturated fatty acid. Now the naming convention for fatty acids is a little different for biochemists than it is for organic chemists. But one thing is certain, that in nature, when you have a double bond introduced into your molecule, say we put one here. The double bond always gives you a cis conformation or a cis structural isomer. In other words, it doesn't go up here like this and then down double bond like that. It goes here, and the trans would be up like that. This like that, like that. But the cis is the natural form of fatty acids. That's what you find in nature. And they're always like this, with this bulky part of the molecule and this bulky part of the molecule on the same side of the double bond. That's the cis conformation. And there's some examples. I don't think we're going to go into naming conventions. No. One thing that is evident from the physical properties of fatty acids is if you have the same number of carbon atoms in the structure and you introduce a double bond, then you simultaneously decrease the melting point. Okay? Remember when these things have two ways to bond with one another, right? They can bond through this acid group, but they can also bond through London dispersion forces with a long chain. So if you have a long chain out here and there are no kinks in it like this, right? If they're just out here like this, then you can line up their neighbors like that, and you can get some pretty substantial London dispersion forces between the two. Now, the longer the chain, the stronger the bonds. But if you put a kink in it, like this, that, and try to line them up, they don't lay with one another correctly. But you don't get the strength of the London dispersion forces that you do with the aliphatics. So that tends to decrease the boiling point because the attraction between the molecules is less. Okay, that's chapter 4. 12:30. Wait a minute. Oh, I was looking at the wrong one. We got till 1:30. All right. I got to get chapter 5 in.
78 flags.
78?
Yeah.
Okay. Do my best. All right, so let's see. And here. Let's say Can I open? Maybe it won't take as long to get through chapter 5. Okay, so let me go back to here and share. That's 4. This is 5. Yep. Slideshow. There we go. Now we talked about the different types of isomers. We got down to stereoisomers. And the stereoisomers, let me see if I can find that schematic. Here we go. The configurational isomers. That is, they have the same connectivity, but as I showed you before, they're connected to the carbon either front back or back front. So that changes the structure of the molecule. And in order to, let's see, we're in chapter 5. In order to make sense of this, we're at the point where they're not rotating around the single bond doesn't change the way they're connected to the molecule. If the molecule is if the substituents are connected to the carbon in such a way that the two isomers form mirror images of each other, and the reason they're called chiral, chiral is from the Greek, which means hand. So they're handed. In other words, you have a right hand and a left hand, right? And the only way, you can't superimpose one on the other. Right? You can twist one around and lay it against it like that. But when you're looking at them like this, they're mirror images of each other. Those are called enantiomers. If they're not mirror images, if the connectivity is the same, but the arrangement around that carbon is such that you can't get mirror images of each other, then those are diastereomers. So it all revolves around the chiral center, the carbon that can produce this configurational isomer, and whether or not you have mirror images. So what that means is, in order to approach this problem, you've got to eliminate the other possibilities. In other words, it can't be a conformer, and it can't be a constitutional isomer. And once you've gotten that far, then you have to decide, is there a chiral center in the molecule? And if there is, then you've got to say, does it produce mirror images, or does it only produce non-mirror images, which differentiates between the enantiomer and the diastereomer. So this example has a substituted methane. Right? It's got 3 halogens on it: bromine, fluorine, chlorine, and the hydrogen. And you'll notice that if they're drawn as a wedge, a dash wedge image, a projection, then you can see the way they're set up there, that they're mirror images of each other. Maybe, I don't know, this will take some extra time, but what if we put together a methane molecule? Right. 4 bonds. This is going to extend . This is going to extend to more complex molecules because larger molecules can have several chiral centers in them. Okay, so I've got that fixed. I'm just going to take 3 different colors. So I got a red here. I got a blue here. Put a hydrogen on this one. And let's see, I need a yellow here. Okay. So what does this one look like? Well, if I use the red, this one looks like the one on the left. What if I make another one? A separate box for these sp2 hybrids. There we go. Ah,
Feelings supposed to have a longer bond.
that's an optical illusion. Well, no, wait a minute. It's a chlorine.
It's supposed to be double bond, is that what those?
No. No, they're all single bonds. Yeah, I think it's just for effect. It's not supposed to have a longer bond. In fact, each one of those bonds should be a different length. Okay, so I'm gonna take this yellow off here, and the red, and the blue. Okay, so if it's connected this way for one, then if I put the yellow over here, like that, and I put the red back here like that, and I put the blue like here like that, oops, and my hydrogen like this, I've got 2 molecules that are mirror images of each other. Right? If I draw a line down through here, they're reflections. This reflected here, that reflected there, and that reflected there, and then the hydrogen. And if I rotate this molecule in any way possible, I cannot superimpose them on each other. Right? If I rotate it where the yellows are on each other, then the blue and the reds are against each other. If I rotate it where the blues are together, then the reds and the yellows. So these are enantiomers. This is a reflected image of that one, but it's not superimposable. All right. Let's see. Every molecule has a, what are they trying to say here? Has a mirror image, but not every molecule has a non-superimposable mirror image. Oh. What we're trying to say here is that these 2 molecules, as shown there, now it has 2 hydrogens. It has a chlorine and fluorine. And the way they're presented, they're mirror images. But if we take the one on the right, say, and we just flip it over like this, then the green and the yellow line up and the hydrogens line up. So that's not a different molecule. It's the same molecule. The point here is that in order to have a chiral center, in order to have a carbon that allows you to make a stereoisomer, the carbon has to be attached to 4 different groups. So with the one we just made here, we have 4 different groups attached to that carbon. If we put a hydrogen here for the red, then they'd be, so they should be the same molecule. Yeah, the same molecule. And they're not, and that's said to not be chiral. They're superimposable on one another, in other words, even though they're mirror images. Okay, guiding principles. Right, well, we know what a mirror image is. I don't need to do that one. An atom and its mirror image are identical distances away from the mirror. Well, that's true. When the mirror is placed next to a molecule, dash wedge notation in the mirror image is identical to that in the original molecule. So here's an example. If we want to draw the mirror image of this molecule, right, we center on the carbon. So the carbon is the same on both sides. And then we need to flip so that we get the other atoms in their proper position. So this chlorine has to be close to the mirror, same distance from the mirror. This fluorine has to be the same distance from the mirror as the other fluorine, and then the bromine also has to be the same distance from the mirror. That would be an enantiomer, a mirror image. Actually, yeah, mirror image. So we can say that if we know the molecule has an enantiomer, that the molecule is chiral. If it doesn't have an enantiomer, then it is achiral. So that's one way of saying that if we know B, then we know A. But if we know A, then we also know B. Right? It's kind of non-issue. How about this one? This will be trans 1,2-dichlorocyclopropane. All right, we see one chlorine is coming out, one chlorine is going back. So does this is this molecule chiral or achiral? Well, if we put it up to a mirror, then the image we draw on the other side, the ring structure is going to be a reflection of itself, but the chlorines have to be exactly the same distance away from the mirror. So that the black wedge chlorine has to be the same red wedge chlorine on the other side, and the dash chlorine on the opposite sides also. Well, what if we rotate that molecule? Rotate the red one 60 degrees. Is it superimposable on the other one? Or if we rotate it 180 degrees the other way, right? It's not superimposable. So we're saying that this molecule is chiral. We can't orient the molecule in any way so that the bond lines and the atoms themselves line up. So the molecule is chiral. Now that deviated from my concept of focusing on one carbon. We were focusing on a ring structure in that one. That we actually jumped way ahead. So what do we mean by a plane of symmetry? Well, if you can orient the molecule so that you can draw a plane through it, and it looks the same on both sides, then you have a molecule that's not chiral. So we look for the plane of symmetry. In this case, we've got a chlorofluoro methane. And if we line up, if we draw the plane through the carbon and the halogens, we get hydrogens on both sides. Right? That's a plane of symmetry. It looks the same on both sides. But if we substitute a bromine for one of those hydrogens, now we don't have a plane of symmetry. That molecule is chiral. All right, so that's another way of trying to decide if your molecule is chiral. Look for planes of symmetry. Okay. This chiral center is also called a stereocenter or an asymmetric atom. So the way I look at it is, for a tetrahedral atom like carbon, if you've got four different groups attached to that carbon, then you have a stereocenter, a chiral center. Let's see. For that example, all we have to do is swap X with W. And now we get mirror images, and they're not superimposable. All right. There's a similar idea. We kept it really simple, right, with these individual atoms. That's easy to see. But you can get chiral centers if you have a carbon that has one hydrogen attached to it and three different carbon chains attached to it. Right? The example here, 3-methylhexane, we have the number 3 carbon has a hydrogen attached to it, has a methyl group attached to it, has an ethyl group attached to it, and a propyl group attached to it. Those are all 3 different groups attached to that carbon. That number 3 carbon is chiral because it has 4 different groups attached to it. And all you have to do to get an isomer out of that is just to swap the methyl group with the propyl group, or to swap the methyl group with the ethyl group. Now, let's see. We don't have, for this trans 1,2-dichlorocyclopropane, if we try to draw a plane of symmetry through that molecule, we don't get one. It has no planes of symmetry. So that means the molecule is chiral. We can divide the ring in half, like bisect the one of the angles of the ring. We would want to bisect. Well, you could try bisecting it through one of the chlorine atoms, or you could try bisecting it between the chlorine atoms. I don't know if they've tried that one. No, they didn't try that one. I don't see why they don't try that. Bisect it through right? Do you have this one? Let's see, like that. And then we have, let's see. This one. Like that. And we have this one. That. And then we draw a line through that. Right? Is that a plane of symmetry? Well, the problem is this one's pointing back and that one's pointing out. So it's not symmetrical. Maybe that's why they didn't include it. How about this one? This carbon, this nitrogen. Right? Is it chiral? Well, it has 4 groups attached to it. Right? How are you going to do that? That nitrogen has to be sp3 hybridized in order to get 4 equivalent bonds to it. So that's a quaternary ammonium compound. 1, 2, 3, 4. Why does the nitrogen have a plus charge? Well, what's the nitrogen has 5? No. Hold on a second. Where is nitrogen? Yeah, it has 5. So we've got 4 groups attached to it. And we're saying that it has plus charge. So how do we know that? Well, the formal charge on nitrogen then would be 5 minus 1, 2, 3, 4 minus 4 equals 1 plus 1. That's where the charge comes from. Now, is it a chiral center? Well, yeah, it has 4 groups attached to it, and they're all different. So that quaternary ammonium is chiral. That means we could swap that phenyl group in the back with the ethyl group in the front. And that would make a different isomer. That would make a mirror image. One example. Okay, what's this one strict rule? A molecule has exactly 1 chiral center must be chiral. Well, yeah, of course. That seems like a no-brainer. Even if the molecule is that big, right? Drawn on the board, of course. If we find 1 chiral center in that whole molecule, that makes the molecule chiral. Now, as a practical matter, chiral molecules have different physical behaviors. One is that 1 enantiomer of the molecule, if you have a pure enantiomer of that molecule, it will rotate polarized light one direction, and the other enantiomer will rotate exactly the same number of degrees in the opposite direction. That's one of the ways that we tell the difference between them. In fact, that's how Pasteur did it. And he had, I think it was tartaric acid, and he could see under a microscope the difference between the crystals. So he separated them painstakingly with little tweezers. And then he redissolved them in liquid and tested their optical rotation of color, and found that one rotated exactly this many degrees that way and the other one that way. Come on. There we go. Okay. So a molecule that has 2 chiral centers could be chiral or achiral. This meso compound contains at least 2 chiral centers, but has a plane of symmetry that makes it achiral overall. So this, are they saying that that is plane of symmetry? Get that out of the way. Oh, yes, yes. A is chiral. because it doesn't have a plane of symmetry. But B is achiral because it does have a plane of symmetry. It has two chiral centers, right? That's a problem that a lot of students have with ring compounds. Trying to decide whether a carbon is chiral or achiral. When you have a ring, you say, in this case, that, like that. And let's see, this one is that, like that, that. Okay, so if you look at this carbon right here, and what's attached to it? Well, it's got a carbon on this side, it's got a carbon on that side, a chlorine on that side, and a hydrogen. So that carbon has a hydrogen attached to it. It has a chlorine attached to it. It has 1, 2 with a chlorine. Has a carbon and a carbon and a chlorine attached to it. On this side, it has a carbon, a chlorine, and a carbon. And carbon. Those are different groups. If we go this way or that way, we get a different, technically a different group. So when you walk your way around a ring structure, you see a difference. That means that one is a chiral carbon. And the same thing for this one. Those are two chiral carbons. But it has two chiral centers, but there's a plane of symmetry right here. Right? That looks exactly like this side over here. So that plane of symmetry says that these chiral centers, in effect, cancel each other out. They may be chiral, but with a plane of symmetry, the whole molecule is achiral. And that's known as a meso molecule. All right, determine which molecule are meso. I think A is meso and B is chiral. Yeah, the one on the left, A is meso. It's achiral. Okay. All right. So now we got to get into a little bit of nomenclature. For molecules that have actually one or more chiral centers, but they're big molecules. If you got more than one chiral center, you've got to be able to distinguish between the two and say which way, what type of chirality does it have? Does it have the attachment this way, right? Or are they swapped and it's this way? Right? There's two possibilities there. So we come up with this designation. We call it R versus S. R stands for rectus, which means rotate right. And S stands for sinister, which means rotate left. The way I remember those is I use politics. If you rotate to the right, you're good. If you rotate to the left, you're sinister, you're bad. Okay? So what do we mean by rotate? Well, we have to assign priorities. And let's see, I don't want to steal my own thunder. Is that coming up? Yeah, Kahn-Ingold-Prelog system. The Kahn-Ingold-Prelog system assigns priorities to the groups attached to a chiral carbon. And I'll give you the rules in a second. But in order to use this convention for properly naming stereoisomers, you start with the overall naming convention that we've already done. And then you decide which are the chiral carbons. And each one of those carbons is designated either S or R. Right? So, and that's tacked onto the front of the molecule. So in this case, the number 2 carbon and the number 3 carbon are chiral. Okay, as it is, the number 2 is rotate left and number 3 is rotate right. But if we swap those, right, if we change those positions for the chlorines in this case, now the molecule becomes position 2 rotates right and number 3 rotates left. Okay, so we need the convention, the Kahn-Ingold-Prelog system. And this can be used not just for the RS, but it can be used later for other priorities. So around that chiral center, you have the different groups, and you orient the molecule. Once you find out what their priority is, you orient the molecule with the lowest priority toward the back. That's usually hydrogen, right? If it's there, it's usually hydrogen goes to the back. It's the lowest priority if it's there. And then the others are arranged in the 3 spokes of a wheel. And then you order them, arrange the substituents 1 through 3 with the highest priority first, and then second and third. And if that priority goes clockwise, that's rectus, right? And if it goes counterclockwise, 1, 2, 3, then it's sinister to the left. Now we need the rules for priorities. Okay. You look at the first atom attached to the carbon. So if we have a carbon with this hydrogen in the back, and then we have something, something, something here. Right? We have this X, Y, and Z. If they're just atoms here, then we look at the atomic number. And the higher atomic number gets the higher priority. If you have isotopes of the same atom, say we have hydrogen, and well, actually, if we have a hydrogen out here, it's not chiral. We put a hydrogen in the back. So if we have 2 isotopes, then the isotope with the higher mass number is the higher priority. If you have several things attached to them, if you have something out here, something out there, and something out there, then we still focus on these first atoms. And we look at what is their, if they're all carbons, right? Carbon, 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 right? Then we need a tiebreaker. And that's when you go to the second atom, right? Y2 or X2 or Z2 and see what that one is. Until you get to the place where you can break the tie. So here's an example. This 6-bromo-1,3-dichlorohexane has the chlorine coming out at us. That means the hydrogen goes behind. Right? So we have these 2 unequal links. The molecule on the left and part of the molecule on the right are different. We have the chlorine, which is different, and we have the hydrogen sticking toward the back. Okay, so now we have this molecule set up. So now the hydrogen is in the back, and we look. compare chlorine, carbon, carbon. Chlorine has first priority. But you've got two carbons, right? We need a tiebreaker. So let's see. Let's go to the next one. Yeah, go to the next one. We go to the next one. And you look at the atoms that the carbons are bonded to. So we go to those two carbons. Now we got the higher priority as chlorine. So now we go to those two carbons. They're both bonded to hydrogen, right? So we can't break the tie with those. They're CHH. So we go to the next carbons out. The next carbon on the left is bonded to two hydrogens. It's CHH again. But the one on the right is bonded to a chlorine and two hydrogens. That takes higher priority. Right. So the chlorine is number one priority. Then the group on the right is the next priority, and the group on the left is the lowest priority. So that would be the way it's written, the way it's presented to us, that would be 1 here, 2 here, and 3 here. So we would rotate like that. That would be R. So that carbon is rectus. It's R. All right. Clockwise. Now, how would we get how would we get S priority? If we left the chlorine where it is, and we took the right-hand group and swapped it with the left-hand group, now it would rotate to the left. And that would be S. Oop, it's 1:15. What do I got? 15 minutes? I don't think I'm going to make it.
Is there any way that when we come in on Wednesday, we can finish up chapter 5?
Let me
Will
see.
that run into our exam?
Let me see about the schedule. Okay, exam on that day, Wednesday. And then we've got videos plus proton transfer to do on that day. That would really be pushing it. The only thing I can think is if you got to go, and I'll finish the recording and post it on Brightspace so that you can review it later. I probably got a lot of slides left on it.
Before on. I mean, you're doing good, but yeah, we still, we haven't.
Yeah. So give me another 15 minutes, and then if you have to go.
I mean, I can definitely finish my, if you're posting the lecture, I can finish it.
Okay. I'm not constrained today. Last time we met, I was supposed to get back for physical therapy, but I didn't make it.
Works. All of us.
Yeah. This happens to me a lot, believe it or not. Okay. So if you have, when you're trying to decide to tie break, if you're going to the second carbon, say, and that carbon is double bonded to another carbon, then you count 2 carbons. So instead of a CHH, it's a CCH. And that would take priority over a CHH. So double bonds take higher priority. Similarly, if it's double bonded to a nitrogen, you get 2 nitrogens out of it for the double bond when you use the Coningold-Prelog method. Yeah, and same thing with oxygens. If you have a double bonded oxygen, then you count the oxygen twice. Triple bonds, you count 3 carbons. So how about this one? Okay, this method is suggesting that if you've got to break a tie, right, you've got those 2 carbons on the right and you've got 3 carbons on the left. When you go to the second carbon, actually, when you go to the carbon on the right and the carbon on the left, the carbon on the right is taken as having more carbons versus hydrogens. So the one on the right is a higher priority. That's what the double bond does for it. And since the one on the right is priority and the hydrogen's in the back, then you go from the one on the right to the one on the left to the methyl group. And that gives you a sinister, an S prefix. All right. Hold on a second. When example, when the 4th priority substituent does not point away. Well, I don't see the problem there. As long as you've got the lowest priority pointing to the back, that puts the 3 in the front. It seems like a no-brainer then. Oh, okay. Yeah. What we're saying is that if you're presented with a dash wedge image and the lowest priority is actually pointing towards you, then you need to rotate it around to the back, which places, in this case, that top image places the one on the right on the left now and places the one on the left on the right as you rotate it around to put the hydrogen in the back. That seems like a no-brainer. I don't have any problem with that. Okay. So if you've got a case where the molecule and its mirror image are interconverting, then we're saying that that is achiral. If the molecule can convert itself, then it's not fixed in its chiral center. So if we get and here they use the 1,2-dibromomethane and give us the what projection is that? Newman, sorry, Newman projection. I think that's a no-brainer. I don't see any problem with that. Do you? Right? I mean, and it just rotates around. That's a conformational isomer, so I don't have any problem. Right? Maybe Dr. Carty has had problems with students understanding when something is chiral and when it's achiral, but if it's rotating around a single bond and I just don't see the problem. I don't see where the interconversion is, though. So I'm going to move on. With a chair flip, how does that change chirality, if any? Well, let's see. If we chair flip this cis-1,2 difluorocyclohexane, we got mirror images, right? Are they superimposable? Yeah, they are superimposable, actually. Just take the one on the right and rotate it around, and they fall right on top of each other. That's what that diagram is showing. All right, so the chair flip doesn't give you a chiral molecule. What about a Haworth projection? Well, if the Haworth projection has a cis molecule, then you do have a plane of symmetry. If you have a trans molecule, then you don't have a plane of symmetry. Right? So if you have a plane of symmetry, what does that mean? It's achiral. Right? And if you don't have a plane of symmetry, then it's chiral. Nitrogen inversions. In this case, we have a molecule that has mirror images. One nitrogen substituted molecule on one side, and the other side is when it's kind of like taking an umbrella and turning it inside out in a strong wind. That's what the inversion is saying. That means that does not make their mirror images, but they're mirror images, but they're not superimposable. Are they non-superimposable? Right, they're not superimposable. So what are we saying? Uncharged nitrogen atoms that undergo nitrogen inversion are not chiral centers. Well, I would look at it this way. Maybe it's wrong, but you've only got 3 groups there. In order to have a chiral center, you need 4 groups. Oh, we're looking at the orbital view, right? So we got that lone pair sticking out there, and in the process of flipping, you unhybridize the p orbital, and then you rehybridize it when it gets on the other side. I don't know how that helps. Oh, now we're talking about diastereomers. These are stereoisomers that are not mirror images of each other. So best example of that is a molecule that has a double bond in it. So you have a cis and a trans version. Those are diastereomers. They're not mirror images of each other. They have the same molecular formula and the same connectivity, but they're different molecules. So here we have, oops, sorry. How'd that get down there? So there you can see that they have the same connectivity, but they're not mirror images of each other. So they can't be enantiomers. They have to be diastereomers. Now they will behave differently. They will have different chemical and physical properties. All right, we have the RS system for stereoisomers in our enantiomers. When we have a double bond, the old system of cis and trans only work if the molecule is well behaved. Very often, the problem is you have that double bond and you have things attached to it that are not identical. If you have identical things attached to a double bond, like say we have chlorine here and chlorine here, or here we have chlorine there and chlorine there. That's very well behaved. We can say this one is cis and that was trans. But suppose we have chlorine and an iodine and a fluorine and a methyl group there. Now, how do you say what? Right? You can't say trans or cis in this case. So we need another system. And the system that's come up is the ZE system. Z and E are the first letters of German words. And we need priorities. So we use the Ingold-Prelog system to establish priorities. And then we say, take the two highest priorities and what side of the double bond are they located on? Right? Let's take this example. Which one's the highest priority here? That one, right? And this one is the next priority. And then how about carbon and fluorine? Fluorine, okay, so that's 3, and that's 4. So the two highest priorities are these two. They're on the same side of that double bond. So that's the Z configuration. Right? It has a German equivalent, but I say these are on the same side. Right? If we put the iodine over here, then that would be the E configuration. Or the opposite sides. Same opposite. It works for me. Okay, so that's another way to, and that also is a prefix to the name as you've learned how to name the compounds. You put that in front. Now, if you have, this is for a single double bond. You only have to just say Z or E. But you can have multiple double bonds. And if you do, you've got to say where they are, like 1Z, 3E. If you have two double bonds in there, you have to say what it is for each one. So here's a situation where we have a diastereomer with no double bonds. Right? In this case, since we have no double bonds, we don't use the Z and E. We only use the Z and E for double bonds. Got to go?
Yeah.
Yeah, good. Do you need a... that's not going to work. Something to hold. Is the lid secure?
Yeah, it's pretty secure.
Okay. You may want to, when you get somewhere, get a nice big rubber band put around it.
Yeah, I want to see.
Okay. We'll see you in a couple of days. So the reason we have to use S and R for these molecules is that they don't have double bonds in them. They do have stereocenters, but they're not mirror images of one another. Right? So the first one has stereocenter at 1 and 3, and the second one has stereocenters at 1 and 3. But they're not superimposable mirror images of one another. So they're not enantiomers. The only option we have for that is diastereomers. And because they are stereoisomers, we have to use the SR system rather than the ZE because there are no double bonds there. Let's see. If two isomers are related by reversing the configuration of all chiral centers, then the two molecules are enantiomers. Okay. We can't reverse these two and make stereoisomers. In other words, if we put bromine on one side and chlorine on the same side, then those would be enantiomers because they would be mirror images, non-superimposable. But since bromine and chlorine are on the same side on one and the opposite sides on the other, then those have to be diastereomers. Okay, 1-chloro-2,3-dimethyl-cyclopentane. Draw its diastereomers. All right. How many chiral centers do we have? Well, let's see. Looks like we have 3. Right. If we take each one of those carbons, which has a hydrogen attached to it, but it has different groups. If you start with, say, the top one, and you work your way around, you find that to the right is a different set of bonded atoms and groups to the one going to the left. And they're also different than the methyl group attached to that carbon. Then we know that that one is a chiral center. And you do that for each one, you find that you have different arrangements around each one of those chiral centers. So to draw a diastereomer, we have to reverse the configuration at some, but not all of the chiral centers. If we reverse the configuration, say we had, let's see, we had that, and we have this one like that. And we have this one like this. All right. Yep. But we have this one. This. And,
Oh, yeah.
huh?
That's chlorine.
Oh, chlorine, sorry. If we made this one dash, dash, and wedge, then that would be an enantiomer of this one because they're all 3 opposite from what they were. But if we just change one of them or 2 of them, say make this one a dash, then they could not be superimposed on each. I mean, they could not be mirror images of each other. So in order to make a diastereomer out of this one, all you have to change is 1 or 2 of them, but not all 3. And you can make a diastereomer out of that. So those are the 2 possibilities, right? In this case, we changed that one for the left-hand side one, and we changed this one for the right-hand side one, but we didn't change that one. So those 2 are the possible diastereomers of that molecule. Okay. So what are we saying here? Because a new configurational isomer can be obtained for each inversion of a tetrahedral stereocenter. In other words, changing this one to dash, that's an inversion. The number of configurational isomers that exist can double with the addition of each chiral center. So it's 2 to the n. If we flip this one, then that gives us another stereoisomer. If we flip that one and that one, that gives us 2 squared or 4 times as many possible stereoisomers. So the number of configurational isomers that you can have is 2 to the n. How many? N is the number of chiral centers. And the maximum number, that says the maximum number of isomers, configurational isomers is 2 to the n. That doesn't mean they're all going to be there, but that's the maximum number. You know, you can't exceed that number, but it could be less. All right, they could be, you could have some meso So if you have meso, then that's not chiral. Okay, so here are the methods for drawing all stereoisomers of a given structure. First, identify all the chiral centers. Be sure you have those tagged. Draw the first structure by specifying the configuration of every chiral center. Use a dash wedge notation to specify each configuration for the first structure. It doesn't matter where you start. Start anywhere you want. I would probably say, right, if I have 3, I'll just make them all wedges and then go from there. Draw the second one by reversing the configuration only at chiral center 1. Then draw the next 2 structures by reversing the configuration at chiral center 2. So it's like a it's like a family tree, right? You start off with this possibility, and then you change one of them, and then you take that one and you change the other 2, and then you go the other direction, you change that one, then you change those 2, and then you can just keep branching. Shades of Darwin, right? In order to develop a set of possible stereoisomers for a given structure.
I'm good to 1.5. I've only got like 5 minutes. To
Okay.
And work too.
Okay,
But
that's fine.
I have a little more cheated.
Okay. So we're going to use this one as an example. 2,3-dibromo-4-methylhexane. So we've identified the 3 chiral centers there. Now those are not carbon 1. Those are chiral center 1, 2, and 3. The first chiral center is on carbon 2. Okay, not to get those confused. So how many possible isomers can we have? Well, 2 to the 3rd power is 8. We can have 8 possible isomers out of this one. Right? So we start off, oh, they're doing what I did. Make them all wedges. Right? And then change the first one. So that gives you the opposite on the first chiral center. The next one, change the second one, and then, well, they're not following the strict pattern that I would. I would have kept B the same and changed the second one, and then put it back and change the third one, and then do both of them. Right, that's the way I would have done it. But however you do it, be methodical about it. Yeah. And eventually you should end up with 8 possibilities. 1, 2, 3, 4, 5, 6, 7, 8. 8 possible stereoisomers. Okay. This one, Fisher projection, gives me fits. Engel Fisher worked with sugars, different types of carbohydrates. And he was trying to figure out how to represent them in a simple fashion so that he could, at a glance, see differences among molecules. So the Fisher projection draws your carbon chain in a line. Right? Carbon, 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 all the way down. And all the side branches are wedges. They point out. And everything in all the verticals point in. Okay. That's easy to see when you only have 1 carbon. That's really simple. And their analogy there, they use the bow tie. But what happens when you have more than 1? Well, if you rotate that XYZW around where W is 90 degrees to the right, then what does that do for the Fisher projection? Well, now what you've said is the Fisher projection, if you rotate it like that, Now, instead of the W being back, it's forward. Okay, so if you try to superimpose them, you can't. So if you rotate a Fisher projection, you're automatically producing a stereoisomer. Assuming all of those groups are different. If you have a long molecule of carbons, then at some point in there, you may have a carbon that's not chiral because everything around it is, at least two of the things around it are identical. But for this example, if you rotate that one, rotate a Fisher projection, you end up with a chiral molecule, a stereoisomer. Okay. The thing about Fisher projections is you can present them in such a way that one may be an enantiomer with another one, but a diastereomer with a different one. And I guess that's the advantage of the Fisher projection, right? If we have D-glucose in the middle and L-glucose on the right, then you can see at a glance that those two are mirror images of each other. But the one on the left, D-allose, is not a mirror image of D-glucose, so it has to be a diastereomer. Got to go?
Yeah, in a minute. Wait 1 minute.
Okay. Now the problem I have, now this is great the way these Fisher projections work. But the problem I have is trying to convert a Fisher projection of these large molecules into a dash wedge. And in that case, you have to think in 3 dimensions, right? The Fisher projection is on a flat screen with all of those cross members pointing out. If that's the case, then in order to make that molecule work in the 3 dimensions, you have to take the molecule and bend it like this in order to keep everything pointing outward. So, since vertical bonds in a Fisher projection point away from you and horizontal bonds point toward you, then the counterclockwise rotation of this example reverses because the 4th priority group points toward you. The 4th priority group here is hydrogen, right? And in a Fisher projection, it's pointing toward you. So the simplest way to determine the RS designation for this molecule is to take the priorities and say what would be the rotation with the 1st, 2nd, 3rd priorities, ignoring the 4th priority because that's the one that's supposed to be the anchor, would go to the left. It would be sinister. But since hydrogen is on the crossbar, it's pointing toward you, it's supposed to be pointing back. So once you determine the RS designation as is, then by moving the hydrogen to the back, you reverse the direction. So you determine it to be sinister to the left. Now, when you move the hydrogen to the back, it becomes rectus to the right. That's the simplest way to deal with a Fisher projection and its chiral centers. Right? So there are 2 ways to go forwards or backwards. Take a dash wedge projection and go to the Fisher projection, or take the Fisher projection and go to the dash wedge. You got to be able to go both ways. Excuse me. So in this case, we only have 3 chiral centers. At carbon 2, carbon 3, and carbon 4. since carbon 1 is part of the the carboxylic acid group, is not chiral. And since the carbon 5 is attached to 2 hydrogens, you don't have 4 independent groups, different groups, then it's not chiral either. So the only chiral carbons you have in this projection are 2, 3, and 4. Okay. Now what we have to do is place the hydroxyls and the hydrogens. So let's see, is that the same molecule we were looking at before? Yes. All right. So what we're going to have to do is take this molecule first and rotate it. Right? So the carboxylic acid is at the top and the methyl hydroxyl group is at the bottom. And then what we're seeing is, let's draw it like this. 1, 2, 3, 4, 5 carbons. 2, 3, 4, 5 carbons. This one has an OH. This is chiral. This is chiral. And this is chiral. And this is OH and O. That's not chiral. So if we draw this Fisher projection and we make this one COOH at the top and this one, CH2OH at the bottom, then we only have 3 chirals here. These have to be pointing out. So this one is going to be wedge, and the other 2 are going to, this is going to be dash, and the other 2 are going to be wedge. Okay. If we rotate this one like that, then this is going to contain the OHs on one of the other side. All right. So rotating this one like that puts let's see, did I rotate it correctly? All right. That means we have hydrogen in the back, hydrogen in the back, and hydrogen in the front. But if we rotate that around, that tends to put the hydroxyl on this side, hydroxyl on this side, and hydrogen on this side. But that's backwards from what they are telling us. Okay, let's go back to the rules. Okay. So around each one of these carbons, they're saying that this one is in the plane. This would be the W on that scheme. This would be the X. This would be the Y. And this would be the Z. Okay. So if we rotate so that this one becomes the top, and the Y is still in the back, the X is in the front. And the Z is in line with the W. Then we want to have this one at the top and facing back. This one at the top and facing back. So if we do that, now we rotate 90 degrees in the other direction. Which brings that molecule to put the Z in the back and the W in the front. And the X and the Y are forward. Okay. So now that means that by rotating it this way and then 90 degrees that way, I think I'm confusing myself. Yeah. Because each one of these lines here, I kind of messed it up. Let me redraw that. So we got this one, we got this one, and we got this one. Okay. If we rotate this in such a way that we want like that, and like this, and like that, we rotate it in such a way that we want these bonds along the carbon backbone to be facing backwards. Then we've got to rotate this around, and then we've got to rotate it this way to keep these in the back, right? Because this carbon, say, fix your attention on that carbon. It's right here. When you bring that out and you rotate it one way, like this, then in order to make these go into the back of the board, you got to flip it again. So that's why the OH goes on this side, and this OH goes on this side, and this OH goes on that side. Okay. I think the best way to approach this is to take the time and build a molecule with your set, with your model set, and then rotate it so that you can see that all of these carbon-carbon bonds here have to be facing back. In order to be facing back, we got to bring it out and do like that in order to make all of those face to the back. Okay. This one should be a little bit easier. Let's see. Convert this Fisher projection to the zigzag. Okay. So let's see. We got a Fisher here with a cyanide on the top. And we've got two chiral centers. And we've got an OH on the right and an OH on the left, correct? Yep. And then a hydrogen here, hydrogen here. So we only have two chiral centers here. So eventually what we're going to do is we're going to have this, oops, sorry. That's nitrogen. We're going to have this CN here on this end. And then we're going to have, there's a chiral center, there's a chiral center, and this one is not a chiral center. So we have one here and one here. And what we have to do is decide like that. Which one's which? All right. When we take this molecule, we know that these are coming out. Both of these are coming out. In order to do that and make these go backwards, each one of these has to go into the board. Then we have to kink the molecule this way to keep these coming out. Kink the molecule this way to keep those coming out. So if we do that and then rotate it this way, then I think this one should be here. Let's see. And this one should be here, correct? Let's see if I got it right. Yeah, actually I did it backwards. Rotate it this way, kinked backwards. The top of the Fisher projection will become the left end of the zigzag structure. Okay. Dash bond because OH appears on the right side of the Fisher projection. All right, they're just telling you to stick with the rules. To convert backwards, if it's on the right-hand side for the first one, then it's going to be dashed. These are dashed. For the second one, you flip sides. Now the second one, the left-hand side is the dash. Okay. So Dr. Carty is saying that you look at your zigzag in such a way that the peak, the first peak you come to, it with respect to your Fisher projection is going to be dashed. And the second peak is down is going to be dashed. So the left is going to be dashed, right is going to be dashed. They go opposite to one another. So if we had another one down here with OH on that side, it would be wedge. Okay. Let's see. Physical and chemical properties. Constitutional isomers must have different physical and chemical properties. That's true. They will have, some of them will have similar, but they won't be exact. So this pent-1-ene and trans-pent-2-ene have slightly different boiling points. Whereas the constitutional isomers with radically different structures, like tetrahydrofuran on the right versus but-3-ene 1-ol, those have radically different physical properties. The mirror images, enantiomers, the mirror images have exactly the same boiling points. Those physical properties do not change. Let's see. Okay. here's the condition. The enantiomers have exactly the same physical and chemical properties if the environment is achiral. So it just means you throw them together into a mixture and you just mix it up and you don't care what happens. But if you change the environment to be chiral, they will exhibit different physical properties. What that means is if you have a mixture of enantiomers and you want to separate them chromatographically, then the stationary phase in your chromatography column must be chiral. All right, so the stationary phase must be chiral. In that case, it will separate them. Diastereomers, on the other hand, they always have physical and chemical properties that differ. So this cis-1,2 dichloroethane is polar because the chlorines are on the same side of the double bond. And the diastereomer trans-1,2 dichloroethane is nonpolar. Right? The bonds are polar between the carbon and the chlorines, but they're opposite and equal, so they cancel one another out. Different boiling points for diastereomers. Here's that reference I made earlier to Louis Pasteur's work with the enantiomers of it doesn't say. I thought it was tartaric acid. I think it's tartaric acid. But he separated the crystals visually. How do you separate them? Well, I mentioned one way to separate enantiomers, right, with a chiral chromatography exchange column. The other way is to modify the enantiomers so that now they are diastereomers. In other words, put them in a chemical reaction so that you change one of the stereocenters to make the two molecules diastereomers. Then you can physically separate them from physical properties. And then you regenerate the enantiomers afterwards, after you separate them. So you add a side group that makes them diastereomers, and then after you separate them, you react them with a chemical that will remove the side group, and now you have your separate components. I mentioned this one earlier also. One characteristic of chiral molecules is that the chiral molecule and its mirror image will rotate plane polarized light in different directions, but by the same angle of deflection. Right? Most light sources emit unpolarized light. You can get on a bright, sunny summer day, you can get reflections off of the pavement as you're driving. That light is polarized. And that's the way that many sunglasses with polarizing lenses oriented just the right way will cancel out that reflection. Because if it's polarized this direction and your lens only lets light through that's polarized this direction, it will block the polarized light coming off the pavement. Now, this optical activity or angle of rotation is characteristic of enantiomers. An enantiomer of one kind may rotate the light to the right. We call it dextrorotary. And the other one will rotate it to the left, levorotary. But they'll always be by the same angle, only in the different directions. Okay, factors that affect that angle of rotation. Right. Well, you have concentration, right? Higher concentration of the enantiomer will rotate more. The angle of rotation will be higher as the concentration increases. The length of the tube through which the light passes will cause rotation to increase. And then there's also a value specific rotation, which is takes those factors into account and prorates the rotation on a standard cell, so to speak. So this specific rotation can be factored into this length of the tube and concentration to give you the actual angle of rotation. What's a racemic mixture? A racemic mixture is a mixture of enantiomers of equal concentrations. So a racemic mixture, which often results from chemical reactions, not always, but very often, will not produce an optical rotation because one enantiomer rotates one way, the other enantiomer rotates the other way, and if they're equal concentrations, they cancel one another out. If, on the other hand, you have a mixture which is not racemic, that is, has an excess of one of the enantiomers, then it will rotate in its favor, but only be partially canceled by the other one. And that's what this formula at the bottom is about. We call it the enantiomeric excess. And then we use the specific rotation and divide that by 100 to give you the specific rotation of the mixture. All right. This particular molecule that's drawn here is thalidomide. It was back in the 50s, I think, 1950s, even earlier, actually, was used, was given to women who were in premature labor, and it would delay labor so that the child would not be born prematurely. What they discovered was this particular molecule, if it is given as one of the enantiomeric forms, causes birth defects. Whereas the other one, actually, I misspoke. It didn't delay. It doesn't delay labor. It suppresses nausea. So if nausea is so severe that the mother is vomiting all the time, give her thalidomide. The problem is, if you give a racemic mixture of the two, then there is a sufficient amount of the of one of the enantiomers that will cause birth defects. So the manufacturer has to be extremely careful to separate this one enantiomer from the other and only use the one that does not cause birth defects. All right. Amino acids. Remember, I drew amino acids earlier. And if you have this alpha carbon in the center, and then you have the carboxylic acid over here, and you have the amine group here, and then you have a hydrogen here, and then you have the R group. If that R group is a hydrogen, then that means that's not chiral center. But if the R group is anything else, then it is chiral. The only non-chiral amino acid is glycine. Like glycine, in which R equals hydrogen, is non-chiral. But all other amino acids are chiral. Glucose is a chiral aldohexose. In fact, it has 4 chiral centers. The deoxyribose in DNA has 3 chiral centers. Testosterone, right, which is a natural steroid, has 6 chiral centers. And usually in the in biochemistry, in the cells, only one enantiomer is desirable or even produced by the cell. So this particular representation of testosterone here, this is the only one that is desired by the cell. Anything else is either benign or it could be harmful. Now, how about these monosaccharides? Some are called D and some are called L. D sugars rotate polarized light in the clockwise direction, dextrorotary, and L sugars rotate to the left. The problem with the DL system is that it doesn't correlate with the SR system. The RS system is unambiguous. In other words, if you establish priorities and set up your chiral center so that you can say rotates to the right or the left, then that's definitive. But D and L sugars, some R sugars rotate to the right and other R sugars rotate to the left. So that's the problem with the DL system. This D-glyceraldehyde rotates plane polarized light in the clockwise direction. So it's dextrorotary. And the chiral center is, oh, okay. So the D-glyceraldehyde is used as the anchor for designating D sugars versus L sugars. You can say D-glyceraldehyde is a 3-carbon compound. But if you add, say, a carbon with its hydroxyl just below the, just below the carbonyl group, then that's the one we focus on. So D-glyceraldehyde has the hydroxyl facing away and the L-glyceraldehyde facing toward us. So whenever you add anything else to it, we base our D and L designation upon that carbon before the substitution. We can apply this logic to not only the sugars, but we can also apply it to amino acids. Only with amino acids, we don't look at the hydroxyl on that carbon. We look at the R group on that carbon, alpha carbon. This makes a little more sense. If the R group is facing toward you, then it's a D amino acid. If it's facing away from you, it's an L amino acid. So here are the families of aldoses, the aldose type sugars, aldehyde based sugars. If we start off with D glyceraldehyde, then we can go, excuse me, we can go, and we're using Fisher projections here, Fisher projections. So erythrose has the hydroxyls on the right-hand side, and the threose has opposite sides. So if we take the opposite sides here and we add another one on top, right, then to the right gives you xylose, to the left gives you lixose. And if we take the erythrose and add another carbon, if the hydroxyls in the Fisher go to the right, then we have ribose, and if it goes to the left, we have arabinose. And you can just keep adding them, and the numbers of sugars that are possible, and these are all D sugars. These are Ds because the original was D glyceraldehyde. Right? And D means that this hydroxyl on the glyceraldehyde points to the right. If we have L-glyceraldehyde, then that hydroxyl's on the left, and then everything else becomes L-threose, L-erythrose, L-allose, L-glucose. All right. It's all based upon the first chiral carbon nearest the hydroxyl, the terminal hydroxyl. Right. So this will be the terminal hydroxyl, and the D and L designation is based upon this direction of the hydroxyl.